Data analysis in Python. This is a continuation really only from our beginning Python course. We've tried to keep the requirements for this data analysis course as minimal as possible to make it useful to as wide a range of people at the university as possible. We don't want people to feel they have to be an expert in Python before they can start using it for making their job and life easier. So we only require a relatively small amount of Python experience. But that said, there might be some things in this course which are new to you. So as we're going through, do feel free to ask in the chat if there's a particular piece of syntax or a particular function that we're using that you're not sure how it works. Please do post a message and ask for a bit of clarification, and we'll try and help out. In order to run the session today, in the previous classes, we've been using Jupyter Lab, which we've installed through Anaconda. Jupyter Lab, we've been writing text files with our Python scripts in, and then running them in a terminal. In the session today, we're going to be using a tool called a Jupyter Notebook. Now, it's possible some of you have used a Jupyter Notebook before, so just to get a bit of a sense of the room, could people post in the chat whether they have or have never used a Jupyter Notebook before? No, good. So lots of people who haven't used them before, so that's going to be the first thing we go through today. Those who have used it before, this first 10-15 minutes or so, feel free to follow through it as well. Otherwise, since all the material is self-guided, you can just carry on through to the next section without waiting for me to get to it, if you so wish. So the first thing to make sure you've all got is Anaconda Navigator, all started up and running. So I'm just going to give you all a minute or so, or 30 seconds or so, to start that up and have it running in the background before I carry on to actually starting the session. Okay, so hopefully you will have Anaconda Navigator started up now and running. It should look something like what I see on my screen here. You might have a slightly different list of apps, or you might have slightly different versions of things, but hopefully it's a similar kind of idea. Now, I said we were going to be using Jupyter Notebooks today. However, I don't want you to immediately click on the Jupyter Notebook launch button. If you do want to use that mode of launching Jupyter Notebooks, it's okay. It's going to work just fine. And if you feel more comfortable there, that's okay. But for the session today, we are going to use Jupyter Lab as the way to start the Jupyter Notebook server. I'm going to explain what these terms mean in a little bit. But if you go ahead on the Jupyter Lab tile, which is probably the first one, and click on the launch button, that should open up in your web browser, one that I prepared earlier, that looks something like this. So I'll just move those to the side so we can see both of them. So click on the Jupyter Lab launch, and that'll open up in your web browser something that looks like this. I'm going to go ahead and make this window here full screen and extra full screen, and the rest of the session we're going to be living inside this window here. So Jupyter Lab is a web-based, I say web-based, it runs entirely on your local computer, but it works in your web browser, even though it's entirely local. And it gives you an environment where you can run Python code, you can write Python code. One of the things it has built into it is its own Jupyter Notebook environment. So the very top icon you should see on your launcher, and if you've been to our previous sessions, you might not be seeing the same view. So just go ahead and you might, for example, have something that looks like this. Just go ahead and close all the tabs at the top. That's perfectly fine. Click on the Python 3 icon under the notebook header, and that will open up a Jupyter Notebook which should fill the whole screen. So having clicked on that Jupyter Notebook Python 3 tile, you should get something that looks something like this. Now this is called a Jupyter Notebook. I'll just give you 30 seconds or 20 seconds or so to get this started up. And again, if any issues, post in the chat. What we have here is a Jupyter Notebook. A Jupyter Notebook is a way of writing and running Python code in an interactive way. And it also provides us with a bunch of extra features which are really useful when we're doing data analysis kinds of tasks. So at the first case, what we can do is we click inside the grey area here and we can type any Python code we like. I'm going to keep it nice and simple. We can print hello. Now, if you just press enter at the end of the line, it just puts another line inside that cell. So it doesn't run the code just by pressing enter. If you want to run this cell, you either click on the plus button just above it up there, or hold down shift and press enter. I'll click the play button this time, but in the course of this session, I'll probably quite regularly be using shift enter or control enter to run the cells. So you will sometimes see me running a cell without clicking it, and that's what's happening there. If I click the play button, it runs that cell and prints hello. It also gives every cell that's been run a number, so you can keep track of which order they've been run in, because in principle it's possible to rerun cells that are further up the page after having run further cells that are further down the page. It can get confusing, and we'll try and cover that later. So I'm just going to switch over to the notes now and copy and paste a few examples from here. So one thing we can do, as I said before, is have code over multiple lines. I'll just show that by typing. So a equals 5, b equals 7, a plus b. If I do shift enter, it runs that cell and displays 12 on the screen. Notice here in this second case, I haven't had to write print a plus b. I didn't need to do this, because the way that Jupyter Notebooks work is whatever the last thing in a cell is will be displayed onto the screen. So here, because a and b has the value 12, it's displayed 12 underneath the cell as the output for that cell. And you see the output and the input have got corresponding numbers. As well as being able to run Python code as we have done in the script so far, it also gives us an extra ability to, didn't mean to make that small, there we go. An extra ability to display output from commands in a slightly more visually pleasing way. Now, don't worry about what this bit of code here does. We're going to be discovering how these things work throughout the session today. I'm just going to make my font a bit bigger. We're going to be discovering how this works throughout the session today. But if you run this, it's going to print something that looks like a nicely presented table of numbers, where you hover over it and the lines get highlighted, which is useful when you have larger tables of data. The thing that's really useful, however, is the ability to display plots. So here, again, I'm just copying and pasting this in. We'll be discovering how these things work throughout the course. If I run this cell with shift enter, we get a plot coming up in line. So if you use something like Mathematica, or I think MATLAB can do this, and R notebooks do this too, it lets you run code and get the output from that code right there, and then you can carry on further underneath and, print whatever you want, and you've got the code in line at the point where you ask the figure to be shown. The final thing that it allows you to do is, as well as having cells which contain code, at the top of the window there's a drop-down menu that says code at the moment, and with this cell selected, if I change that to say markdown, if I click on the markdown button on the drop-down menu, you see the square brackets at the beginning have disappeared, and now this won't accept Python code and run the Python code. It will instead accept markdown. Now, markdown is a way of applying formatting and design to plain text. So you can start headers by doing a hash key, and you can write header. And then if we run that cell, you see it turns the word header into a big word header. You can then double click on it to edit it. You can write bold text and italics, or I could if I could spell correctly. And you see it formats it with bold and italics. And so what this allows you to do is to interlace with your code blocks of text which describe what your code is doing. And the real powerful thing about this is it gives you the ability to write a whole report with introduction sections, bits explaining your science or whatever it is that you're doing, intersperse that with the code which is executing your analysis, and take that whole report and compile it to something like a PDF and allow you to give that out to people as, this is all the stuff I did and the code's all in there as well. On top of that, it also allows you to give the notebook to other people so that they can take this report you've written and they can run it themselves and see if they can reproduce your outputs. A particularly famous example of this, though it's becoming more and more common these days, was the LIGO collaboration, when they were looking for gravitational waves, published all of their results as Jupyter Notebooks, with the data provided alongside them, so that people around the world, citizen scientists, could download these files and run the same analysis that was performed by the people at the LIGO collaboration and see if they could reproduce the science, have a go at tweaking the numbers, playing around with things, and see if they could discover anything in there as well. So it's a really good way of getting engagement with people outside of your local small field and giving them the ability to play around with the code there and then. So there was a question in there that's now looking fine. So yes, there's a question there about the plot not showing up. There's two things. Firstly, it sometimes takes a few seconds for the plot to appear because it's running the code. Secondly, you sometimes have to run the cell twice for a plot to appear. That's supposed to be what this magic little line at the top means, that you don't have to run it more than once. But if your plot doesn't show up, just run that cell again and it should then show up. So to give you all a chance to have a little play around with Jupyter Notebooks, I'm going to scroll down to the bottom of that first page in the documentation. And there's an exercise there, which contains a block of code. So what I'd like you to do, just for a minute or two to get a handle on this stuff, is to copy that code into a few cells in your notebook. And I'll just switch back to the notebook a second. You can add new cells if you click in a cell by clicking the plus button at the top. You can add as many cells as you like by pressing that button there. So I want you to take this block of code, split it over multiple cells, and in between some of those cells, add a little markdown block, which describes just in a few words as a comment what the next little line of code does. I'm going to be going through that on the screen myself just to give you an idea of what that demonstration looks like, and I'll just give you a few minutes to have a play with that yourself. Kunal asks, is there a shortcut for adding cells? Yes, there is. So when you've got a cell selected and the cursor is flashing inside there, if you press escape, you'll see that the cursor has disappeared. It's no longer flashing inside the cell, but the cell is still selected. In this mode here, if you press the A key on your keyboard like this, it puts another cell below where you are. And if you want to add a cell above where you are, you can press the B key on the keyboard, I think. Yes, press the B key and that will add a cell above where you are. How can I go back and rerun? So if you want to, well, you can move up and down with the arrow keys. If you want to rerun all of the cells from the start, if you go to the kernel button at the top, and there is a restart kernel and run all cells button, and that will get everything rerunning from the beginning. So yeah, just take a minute or so now, just have a play with that example, and I'll do the same in my window here. And again, any questions, please do post in the chat, and one of us will be there to help you. Olivia asking, how did I add the text bit? If anyone's happy carrying on, just carry on for the minute while I answer some questions. So, Olivia, if you select a cell so you've got it blue like this, at the top here there's a drop-down menu. By default, code is selected because that's the default cell type. Change that to markdown. And one thing you'll see happen is that the square brackets in front of it disappear. So that's how you know you're in markdown mode and not in code mode. Click inside the cell, and there you can type something like header. So a hash and a space at the beginning of the line makes it a header. 2 stars makes bold, and an underscore makes italic. And if you use the back tick key on your keyboard, which everyone's keyboard's different, but in mine it's in the top left, you can write code block like that. And I'm just going to copy that into another cell so that we've got the example and the real one. So this code here generates something that looks like this underneath. Does that answer your question, Olivia? Great. And Rob, your cells aren't showing the answers after running. So if you could post in the chat there what you've typed into your cell, and then I'll see if I can reproduce it on the screen. Okay, I'll come to you in a second, Kunal. So the first 2 things in the exercise, if I copy those 2 lines there, for example, and I type that into a code cell, if I run that cell there, you're saying you don't see any output. And that's correct, you don't see any output, because in this case here, the last line of code, and I say line in inverted commas, I know you can't see me, but I am, the last line of code in that cell doesn't have a value, because it's assigning it to a variable, and the act of assigning something to a variable in Python kind of soaks up the value that you would have been passing in. And so this line of code here doesn't have an output of any kind, it's just performing a side effect. And so you don't get any output from here. If we put in this cell my purchases, and then purchase, there we go, and run that, there we do get an output because that line has a value. And Kunal, how would I tell Jupyter to run several cells together? So, I don't know, let's try something. If I select two cells at once, which I can do by clicking on one, holding down Shift and clicking on another. If I press play, it looks like they both run. So you can select a cell, select another cell with Shift Enter or Control Enter, I think works, and then press the play button and both of them should run. However, the easiest way to get that to work is to go to kernel at the top, restart kernel and run all cells, and that will run everything. Okay, so a question here about the other things in this drop-down menu. So you see one that says raw. That basically, in the mode where you want to generate a PDF, Jupyter won't do anything to the cell before just putting it in the PDF. So it's just really, really basic and raw. So you never need to use that one. Heading, I don't know what that one does. I'm guessing it's just a shortcut for a markdown cell. The only two cell types I ever use is code and markdown. That's all I've ever needed. Okay, so hopefully you all had a chance to have a little play around with the notebook. It does take some getting used to. I do strongly recommend getting used to using some of the keyboard shortcuts. So it's going to make your life a lot easier if you keep your hands on the keyboard rather than moving around. So for example, I'm in this cell here. I can press Escape to deselect the cursor, press up on the keyboard, and then press Enter, and then now I'm typing into the cell above. If I press Escape there and press B, I'm now in the cell below. I can press Enter and then type A equals 7, for example. I can run that with Shift Enter, and then I can move down to the bottom cell here and then run that cell again, for example. I've done all of that without touching the mouse at all, and that's going to make your life easier as you become more accustomed to using Jupyter Notebooks. Okay, so moving on to the next section here. First thing we're going to do is in the notes, at the bottom of every page there's a next button. Go ahead and click on that next button now. And in general, Christopher will probably be posting into the chat the link to the current page we're on. But in general, you should be able to just follow through in the order I'm going. I think Christopher might be helping someone with a question at the moment. So, introduction to Pandas. So this course is about data analysis in Python because it's a very, very common thing that people in all walks of the university have some kind of data they want to analyze. Maybe it's in a spreadsheet, maybe it's in a text file, maybe it's downloading from a website. Often what they want to do is ask a few questions about it, for example, to select a subset of the data or to merge it with another form of data, and often to plot a graph at the end. A lot of science comes down to a bit of analysis and plotting a graph, as I'm sure you're all aware. So the idea of this course was to get people to the point where they can do that set of tasks without having to do sort of too much complicated things. We want to kind of find a critical path to getting the solution done. So in Pandas, the primary tool that provides these features that you need to do those things is a tool called Pandas. Now Pandas is a third-party module. It's not core Python. It's written by people around the world, writing stuff in their own free time, written by people like you and me. But it's included by default in Anaconda, which is one of the reasons we use it. But the reason it's included by default in Anaconda is because it's by far one of the most popular Python packages out there. It provides a couple of basic pieces of functionality. The first of which is a series, which is what we're going to be covering first. And the second is a DataFrame, which we'll come on to in a little bit. But to get a little sense from people in the room, could you let me know if you've ever used Pandas before? Or if you've ever done anything with Pandas or just had to work on code which has used Pandas before? So we're seeing a few people with yes, a few people with no. Okay, good. So lots of people have never used it before. You're the perfect target audience. However, those who have used it before, hopefully we'll go through some things which will clarify stuff, explain how stuff works underneath. And again, if there's anything that you're really comfortable with, feel free to move through a little bit faster or ask questions about how you can do other things about it in the chat. Yeah, so a few people have used it. Most people haven't. Wonderful. As I said, Pandas provides a few different tools. The first of which is the series. Now, a series in Python, in Pandas, sorry, you can access by importing it from the Pandas module. So I'm going to start a new notebook, and I'm going to do that by clicking on the plus button up in the top left where it says New Launcher, and I'm going to select a Jupyter Python 3 notebook. I'm going to save and close the old one because we don't need that one anymore. And I'm also going to rename the notebook by right-clicking on the tab at the top, select Rename Notebook, and I'm going to call this Pandas. Giving your notebooks a sensible name is a good idea because just having everything called Untitled 1 and 2 and 3 isn't going to make your life very easy. So we start off by from Pandas import series. So from the Pandas module, we're importing the class series. I run that with Shift Enter, think about it for a moment, and we've got access to a series. I'm going to copy this line of that list because otherwise I'll get a different set of numbers to you. So the way that you create a series in Pandas is by calling the series class like a function, and you can provide any list of data to the series object. Because at its core, the series is kind of like a Python list. It works in a very similar way superficially, and we're going to be investigating some of the differences shortly. So the easiest way to make a series is to give it a list of numbers. So here inside the round brackets, I've given it a list of numbers with the square brackets. These are all integers in this situation. If I run that cell, it's going to, because I haven't assigned it to a variable, it's going to display the value of that object. And this is a view we're going to have to get very used to seeing. We're going to be seeing a lot of series, or whatever the plural is. So I'm going to explain now what the things on this screen mean and what we should be paying attention to when we see them. Now, the first thing you hopefully notice is that this line of numbers on the right-hand side are the same numbers and in the same order than those we passed in the list at the top. 14, 7, 3, minus 7, and 8. So the first thing to notice is that series has maintained the order that we pass things in, and that makes sense because you'd hope that a series is serial and maintains ordering. The next thing to look at is on the left-hand side, we have the numbers 0, 1, 2, 3, 4. These are the index. You can think of these as being the row number or the row label, because we'll see in a while that the row label can be strings as well as being integers. Because we haven't told it what labels we want to apply, it's automatically generated the numbers starting from 0. Because remember that Python always starts counting from 0. The final thing to be aware of is the D type. D type means data type. In this case, it is an int 64. Int means integer. 64 means it's a 64-bit integer. 64-bit integers can get very large. They can get as large as 2 to the power of 64. So the largest integer you can have inside this thing is pretty much that big. Except actually it's only that big because it goes positive and negative. So you can hold very, very large numbers inside here by default. The reason that it tells us what the type is here is because Pandas is going to use the type of the data to perform certain optimizations as it does stuff, which is useful when we're dealing with millions of numbers and we want to do mathematical things to them. It's going to do it nice and fast. As I said, here we didn't specify an index, so it generated one for us. We can go ahead and give an index to it. Index equals, so as a second argument to series, we pass a list of, well, whatever you want. But here I'm going to use a couple of strings, single character strings, but strings nonetheless. And when we run that, we see printed out on the screen the same numbers as before, but here we have a set of indices. Just take 30 seconds or so now just to have a go at making sure you can import pandas, you can generate these series, and I'll be back in a moment to carry on with the next section. Okay, got a question there in the chat from Dan. Is it impossible to index from a sliced range? Okay, so you're asking, for example, if you wanted to do something like, you wanted to have the numbers, sorry, something like 1 to 6 in there. That's fake syntax, that won't work. So if you wanted to do something like that, you should be able to use the range syntax and do 5, 10, and that will give us, nope, am I missing a bracket? Oh, because it's a comma, not a colon. There we go. So in the index there, I passed in the range function, and so it started from 5 and gone through to 1 less than 10. Is that what you meant, Dan? Great. And Adam, is there a shorthand for copying a previous line? Yes, there is. So if you've got a cell selected, you press escape so that your cursor's not in there. I think if you press Y and then P, Y and then P. Nope, someone said there's a help if you need it. Edit. Copy is C, paste is V. Okay, so you select it, you press C, and then you press V. There we go. So C to copy, just pressing the C key by itself, and then V to paste. And you can delete a cell with pressing D twice. I'm not expecting you to remember all of these. There is a way to get the keyboard shortcuts, but I can't remember how you do it. It's probably in there somewhere. If anyone can see how to get the Jupyter Notebook help up, then that would be great. Okay. So let's go ahead and actually do something with these things. So I'm going to go back to, actually, which one? I'm going to try and keep up with what I've got in the notes. I'm going to go back to this cell here. So I'm going to delete these other cells. So we have here a series. I'm going to assign that to a variable s because I'm unimaginative. And see, this time, because we've assigned it to a variable, it hasn't printed anything out. But we can have a look by writing s, and then it shows up on the screen. Escape and B to do another cell, or press the plus button there. So we want to ask something of it. I said that series are like lists, and they are like lists in many ways. One of which is that you can use square brackets to select items out of them. And in this way, they're actually starting to act a little bit more like dictionaries, because we don't put a number in here per se, although you can if your index is a number. You put in here the row label that you want to select. So in this case here, because we labelled them A, B, C, D, and E as strings, we can pass in here C. We run that, and it gives us back C is the third item, C is the third item, so C gives us what happens to be number 3. If we do it with A, we get 14. So it gives us back the value from the list, from the series, sorry. If you're used to R and their pandas, their data frames and so on, they would give you back a list with one item in, which is 14. However, Pandas just gives you back the number itself. So it's saying that the value from this list associated with the value A is 14. We're going to see later on some more advanced things that you can put inside these square brackets. But if you just put a single item by itself, it's going to look up that row, find the index label that matches it, and return it back to you. You can also edit in the same way. So we can do S and we can edit, let's edit E, and we can set the value to be something else. So we can say this should be minus 999. Run that, it's done it. New cell S, and we see that E has been updated and changed. So there's 3 exercises after this bit here. Don't necessarily worry about doing all of them. In general, there's a few more exercises than you really need. They're just there to stretch you if you're interested. Just take a minute or two to have a go at those, and then I'll move on to the next bit. Right, it's a question there from Adam in the chat. So compared to MATLAB, this is basically a way of storing data, but can we add in strings as well? You absolutely can. So in the examples here, I've been having integers as my types here. If I take my series example and make a bit of space and do it here, you can absolutely put this is a word, and actually let's run it without the S at the beginning, and you see we've got some data here which is, this is a word. So you can put any kind of data in here at all. You'll notice this time the D type has changed to object. That's its sort of generic, I don't know anything more than it's some kind of object. That means that you're losing the ability to have efficiency and speed when you're dealing with these things. So if you wanted to do mathematical operations to this series, it would become slower than it would be if they were all integers, for example. In general, it's a good idea for each series to have one kind of data, so have these all as strings or all as integers or all as floats, but it is possible to mix them together. Suddenly my shortcuts stopped working, so if your shortcuts won't work if your cursor is flashing there, so if you want to, for example, copy or do a cell underneath, make sure you pressed escape so that the blue outline around the cell disappears and it's just grey and there's no flashing cursor there anymore. That means that when you do something like A to do a cell above, it works correctly. So give that a go and see if that helps. And I'll delete that cell. So from those exercises we've just been going through there's a question there about how does a Pandas series differ from a list or dictionary? And while these ones above are just having a play around and having a go with these things yourself, I'll answer this question about how a series differs from a dictionary and a list. I wanted to point these out because it's useful to have an understanding. Because one of the things you need to get used to in programming is choosing the right kind of container for the data you're dealing with. And so knowing how they compare against each other is a useful first step along that. So they're like dictionaries because you can just access by any kind of key. But importantly, series are ordered where dictionaries aren't. We'll see later on that series can have repeated indices. So while you can't have a dictionary with the same key repeated, you can have that in a series. It's generally not a good idea, but sometimes it does make sense, so be aware of that. And series are sped up and made fast by using numpy or numpy behind the scenes. A list, again, they're in order, and you can index by integer in principle, but a series lets you access stuff by key, as we saw, and again, it's made faster. So on the whole, it takes the best bits from both and makes it faster, but there are some situations where you don't want something quite as difficult to interact with as a series. It's not built into Python, for example. So, series operations. Let's have a look at an example, and I'm going to be asking for some audience participation in a moment. So here we have a list. If we wanted to double all of the items inside that list, let's do something like my list times 2. Now, could you post in the chat there and let me know what's going to happen when I do the list multiplied by 2? Is it going to double all of the numbers? And you can cheat by trying it yourself. Yeah, okay, good. Lots of people saying yes. Let's see what happens. Oh, that's weird, isn't it? So because this is a built-in Python list and not a series, it isn't making the assumption about it being numerical data. A Python list is just designed as a container for information. So what it's actually done is it's taken our list, 368,410, and it has doubled it. And it's doubled it in the most literally minded way you can imagine. It has just repeated itself again. If we wanted to double every item in the list, we'd have to manually loop over it, put the doubled items into a new list, and that takes some time. And takes some lines of code as well. With only 5 items, you're not really going to notice any slowdown. But if you have 1 million items, putting it in a Python list and looping over it is going to be slow. So let's take this same list and let's make a series called S. In fact, let's call it S1, so have this different name from before. And so we're taking our list, we are converting it into a series and giving it a name. S1 now looks like this. So it's those same numbers, but it's a Pandas series. If we multiply that by 2, it's done the correct thing. So it hasn't duplicated the list, it has applied this operation to each item in the list. And because it knows that they are integers, it is able to do this in a very, very fast and efficient way. Right, so the code will go green. Yeah, so while it's running, it goes green apparently. So that's the difference between the two, David. So this allows you to run this numerical operation on everything inside this list. Now, this is useful if you've got numbers inside there and you want to be able to double them or find averages or things like this. But as well as doing numerical operations like times 2, or we could do minus 2, that works too. So 3 has become 1, 6 has become 4, etc. We can also do Boolean operations, so logical questions about our data. So instead of doing a mathematical operation which changes the numbers, we can ask questions which are going to give us back true or false answers. So for example, we can say, is S1, I'm going to change this cell here just to be S1, so we've got a reference, is S1 greater than 6? And we run that, and it gives us back the answer, but it's giving us back the answer for every single row. It might look like we're asking the question of, is this whole series bigger than 6? But actually what this ends up meaning, I'll just scroll down a little bit, what this ends up meaning is for each item in the list, ask each of them, are they greater than 6? So 3 is not greater than 6, 6 is not greater than 6, 8 is, 4 isn't, 10 is. And so it gives us back this list of trues and falses. There's a question there from Olivia. So this means in lists I can only do these kinds of operations through looping. Realistically, yes, there are ways to make it look like you're not looping, but you are always looping. So what this has given us here is ability to ask these questions and get back trues and falses. You see that the D type has changed to bool for Boolean. We'll see in a moment how we can actually use these ourselves, but have a quick go now. Just have a play with the series. Try doing multiplications on them and try doing greater thans, try less thans, or equals tos, and things like this, and see what works, and see if you can get stuff to give you output that you expect. And I'll be back in a few minutes to move on to the next bit. Jeanne's asking, how do you get just the numbers from the series? So you want to get not all of the stuff around it, you just want to get the values, and you can get that by writing dot values. And that gives you back the array with just the values out of there. Okay, great. So a few good conversations happening in the chat there. So Bo's asking, is numpy faster than pandas or not? So pandas, as Christopher says, uses numpy behind the scenes. Everything underlying it is numpy, and it's just using pandas as a way of giving a nice interface on top. Yeah, as Christopher says, always one step ahead of me is he. I'm going to go, again, I'm going to just make some more space underneath, and I'm going to come back to our S thing from before. I'm going to change S so that the last item in it, actually no, I'm going to redefine it so that it's the example from before. There we go. So, S, A, B, C, D, E, and the numbers. I showed you before that with an S you can do something, oh dear, you can do something like S is greater than, let's say, greater than 4. And it gives us back some trues and falses. Now that's useful as a first step. It gives you something which, if you look at with your human eyes, you can see that there are trues and falses, and so you could kind of try and cross-check, and you could say, okay, so which items are greater than 4? A is true, B is true, and E is true. Okay, so that, and that have passed my test. Okay, that's good. However, we are lazy because we are programmers. The best programmers are always the laziest programmers because we make the computer do the work for us. We shouldn't have to do this manually because software is there to automate our lives. So I'm making another cell below. I'm going to take this S greater than 4 thing, and I'm going to kind of double things up. I said before that when you write S and you put brackets in it, you can put inside here something like A. The spaces here are just for clarification in a moment. The S's here are to, the A here is going to select row A from S. So I said if you put a single item in here, it's going to give you back that single item. However, there is a special shortcut mode that if you put inside these square brackets something that is a list of trues and falses, or more specifically a series of trues and falses, it will use that series of trues and falses as a mask. And anywhere where there is a false, it will not show the data. And anywhere where there's a true, it will show the data. So here we can paste in our S greater than 4. So S greater than 4 is inside those square brackets. And when we run that, it gives us back just the things that passed the question. Now this here is obviously a simple example. It's just asking a small question about your data, is it greater than 4? But you can ask more complicated things. You can say, if s is multiplied by 2, is it still greater than 4? And here we see that we've got extra data has come through. Now while c, i.e. 3, isn't greater than 4 itself, if you double 3 to 6, 6 is greater than 4, and so it passes the test. And so you can put relatively complex questions inside your square brackets here, and that's going to give you the ability to filter down your data and discover the things from it that you really, really want. Hopefully throughout the session today we'll be seeing more examples of this, but at this point I want you all to have a go at doing that yourself. Have a play with the putting different numbers in here, try making different series yourself, and see that you can reproduce this and make sure you understand how it works. If any of you have any questions about what this does, how it works, or what kind of extent you can take it to, please do have a chat with us in the chat there. And apart from that, I'll be jumping back in again in a minute or so. Okay, so hopefully you've all had a chance to have a little play around with querying your data like this. There are other ways of querying data in Pandas. We'll be seeing how they interact with larger forms of data in a short while, but there are also other techniques out there. I do recommend having a look through the Pandas documentation after this session. Some of it is very technical and dense, but some of it is written for relative beginners, so you should be able to get some useful information out of it as well. I'll point you towards it towards the end of the session. So the last thing I wanted to cover on series, which is going to be useful later on, is how you can do things between two series. So here I've defined two more. I've got S2 and S3. One's got largish numbers in it and the other one's got smallish numbers in it. As before, we saw that we can do S2 minus 5. That subtracts 5 from all of the values inside S2. So 23 goes to 18, for example. But if you've got two series which are the same length, you can do S2 minus S3. And it will subtract the corresponding elements from the two of them. So it does 23 minus 7 is 16, 5 minus 6 is minus 1, and so on and so on. And again, it does this very quickly. It will, even if you've got like a million items inside here, it will be able to subtract one from the other in a fraction of a second. So you generally don't have to worry about the speed, as long as your D types are showing up correctly as int64. And as long as these are a similar size thing, this is always going to be a nice fast operation. You don't generally have to worry about that. If you do get to the point of having to worry about your data being far too big, we'll give you some information at the end of the session to come and talk to us about how you can get help after the session. So moving right down to the bottom of this, what was the title of this page? Was Introduction to Pandas. Moving right down to the bottom of that page, there is a final exercise here, which I will just go through with you. So create two series of equal length with no specified index and containing any values you like. Perform mathematical operations on them. That's what we've just done there. Now what happens if they've got different lengths? Let's have a look. So let's make S3 shorter. So S2 we've got 5 elements in, S3's now only got 4. If you subtract one from the other, I didn't run that cell again. Classic thing that happens, if you change a cell but don't run it, then the values that are set inside it don't get updated. So you have to make sure you always run a cell after having edited it. So here we see that S2 minus S3 is done 23 minus 7, again, 16. 5 minus 6, minus 1. All the way down till it's got to 7 take away 4 is 3. Then it's trying to do 5 take away, well, there's nothing there. And it's important to be aware of the difference between 5 take away 0 and 5 take away... And at that point I just paused, because there's nothing to subtract from it. There's no definition of what you, if you do 5 take away something that just doesn't exist, what the answer should be. It's not 5, it's not infinity, it's not anything. So to handle this situation, Pandas and generally most Python and other programming languages have a type called nan, which stands for not a number. And so any situation where you do something that represents something that isn't a valid number will put a nan in its place. Now nans are viral, So if you do nan times 3, that's going to be a nan. If you do 5 minus nan, that's going to be a nan. So nans become sticky and they hang around. Another good question in there from Anna. Why are they floats now? So I was about to come on to that, but I'm glad you pointed it out. So 23 minus 7, integer. We've clarified they're integers from before. But now for sometimes it's 16.0. And for the pure mathematically inclined out there, you might think that 16 and 16.0 might be technically different things, and they are in programming languages. The reason it's had to do 0.0 here and turn them into floats, and you see it's a float 64, is because the whole column of values has to be of the same data type, and there is no way to represent nan inside the integers. Integers go from minus a big number to positive a big number, and there's no bits of information left over to represent nan. Floats, however, do have a special little set of bits built into them which represent nan. So as soon as your column gets nans involved, your numbers are going to turn into floating point numbers. Now, some of you might not be seeing floating point numbers here because this is one of the things that's changed with the recent release of Pandas 1.0. It's now a little bit different, and you can have integers with nans because they do something a bit cleverer. So in the future, this might not be happening, but it's worth being aware of. Okay, good. So with that, we are going to move on to the next section. At the bottom of that page, there is a next button. And we are on to DataFrames. Now the term DataFrame, as far as I'm aware, was stolen from the R programming language, either from the language itself or from one of the packages, I'm not actually entirely sure. At its core, you can think of a data frame as a table of data. So a series is a one-dimensional list. It is something which just goes along in one direction. They are originally technically designed, I suppose, for use as time series. So in our examples before, we had indices which were numbers, automatically generated 0, 1, 2, 3, or A, B, C, D. But you can have an index being a complicated value, like a timestamp. So a series might be used, for example, to store all of the samples from an experiment. Maybe that's all of the temperatures throughout a day, or all of the atmospheric concentrations of CO2 throughout a year. That's a one-dimensional set where there is a one piece of information, but repeated, and each piece of information, each row, has a label saying when it was collected. So that's what a series is. A data frame is a table of data. And so where you can think of a series as being a column, a data frame is a set of columns all connected together. At its core, a data frame is made up of a bunch of series put next to each other, making up a table. That's what they do. And as soon as you start operating on data frames, start asking questions from them, you are going to start getting back series. And this is why we've started with the simpler series type, because very quickly data frames devolve into a series, and that's how you start operating upon them. So we'll start by importing this, and I'm actually going to start a new notebook. I'm going to save the old one, but I'll leave it open. I'm going to start a new notebook, and I'm going to call this one DataFrames. And we start by from pandas import data frame. Now, there's a question in the chat about how often do you have to do this import. Generally, you do it once at the very top of your notebook, and then it persists for the rest of that session. This next bit I am going to copy and paste, because there's no way you want to sit here and watch me type out all of this. That would be very boring for everyone involved, and I would absolutely definitely make a mistake. So this is just a plain old Python dictionary. Each key is a string, and each value is a list of items. Each of these three lists are the same length. The way this is going to work is each key is going to be used as the label for a column, and each value is going to be used for the values in that column. So we go ahead and run that. Now, at the moment, that's just a plain old dictionary. If you want to turn it into a data frame, we should go ahead and use the, if I could spell, data frame class, which we've just imported at the top, and we pass it our data in the same way we passed our series, our list, to the series. There's a convention to name your data frame df, and that's a bad idea because it doesn't describe it, so I'm going to rename this to census. I think that's how you spell census. Then in the cell below, I am going to print it out, census. You're going to see me lots of typos in this session. There we go. Just going to make sure I've got my chat window open. Good. So you can see here, we've got a table. We hover over it and we see all the lines showing up nicely. So I didn't mean to scroll there. We've got 3 columns because we had 3 items inside our dictionary: city, year, and pop. City, year, and pop. In the city column, we had Paris, 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 and then 4 Londons and then 4 Romes. We see the same thing here. So it's maintaining the order of the data. At this point, we don't care about our dictionary anymore, so I'm actually just going to scroll down to the bit that matters. We've taken our data, we've printed it out. You can think of each of these columns as being a series, and you'll see there are 3 columns, so there are effectively 3 series being involved here. If you remember before, every series had its own index. The way that a data frame works is it combines all the indices from the parts together and gives one overall index all the way down the left-hand side. And now, because we haven't specified an index, it's assigned one for us. Again, the integers displaying from 0. So I'm just going to give you a few seconds now just to copy and paste and run that code yourself. Make sure you can import the module. Make sure you do this line here. And make sure you can get to the point where you've got a table displaying in your code. So give you a little bit of time there just to have a go at that, and then I'll jump back in. Okay, so I'm not seeing anyone shouting for help in the chat, so I'm going to assume that on the whole things are working well. And again, if I'm going too fast or too slow, please do say something. So there's a few things that we can do with these data frames. First of all, you see this data frame here already fills up most of my screen. I do have my font size set quite big, but it fills up most of my screen. In the case that you've got hundreds or thousands or millions of rows, this isn't going to be tenable. So one thing you'll often want to do is just have a little peek at the first few rows of your table, just to kind of get a sense of how it's looking. And we can do that by writing census.head, and then you give a number of how many items you want from the head of the table. In this case, maybe 3, and you see it prints out the first 3 items. Similarly, you can do, tail, head and tail, beginning and end. These are quite common terms in programming languages, so you'll see these cropping up a few times. The other thing that we want to be able to do, and it's going to lead into some of the really powerful stuff we're going to be doing throughout this session, is grabbing data out of our table. So we start with our census. With our series, when we put stuff in square brackets, if you remember, it would select by row. So you might think you put census 1 and it would give us out this row here. But actually, the way that data frames work is that they select by column first. So in here, we have to write something like city. That will give us back the city column. So to reiterate that, a series selects by row, a data frame selects by column. That's half true, and I'll explain exactly how this can get more messy in the future. If you remember that we selected by row in our series, but we could also put in those questions with the trues, falses, and that worked too. And we'll see things like that carrying on being the case. But on the whole, if you just put a single item in, it's going to look for a column by that name. And if we look for something which is not there, it will give us a big scary red error, which if you scroll down says key error not there. That's it saying there's nothing by that name. So let's go back to city. This has given us back a series, exactly of the type we were dealing with before. The only extra thing it's got is now it's got a name. It says name city, and so we can remember which column it came from. We can check the type of it by wrapping the type function around it, and we see that it really is a pandas core series object. So that means we know exactly how to deal with it. So let's start through that again. Census, square brackets, city. So we could say something like, I want to select all of the rows where the city is Paris, because those are the census informations that I want to do my subset of my analysis on. Because this is a series, we remember before that Boolean operations on series give us back a list of Booleans. We expect to get the same thing. And we do indeed get a list of trues and falses, where the trues are the rows where it was Paris and the falses are elsewhere. Now, as before, we can take anything that's a list of trues and falses with associated indices, an object like this, and like before we passed it into S. In this case, we can pass it into census. And inside those square brackets, I'm going to copy and paste this thing here. And the reason I put those spaces around it is because the proliferation of square brackets can get confusing. So these outside square brackets are asking a question of census, and so they're going to give us a subset of census. These inside square brackets here are selecting the column on which we're asking this question. So this here is a list of trues and falses. It's going to mask and select down just the rows from the census table, the thing up above, which match this question. And so when we run this, we get back just these items here, which match Paris. Have a little go at that yourself, make sure that's working, and then I'll carry on to the next bit. So we selected here census, and to select a column out of it, we just put something in the square brackets. It's quite common that you actually want to select by the row index. And so to do that, you do .loc, which stands for location. Not the best name I know, but it does work. And if you put the number 3 in there, it's going to give us back the row that matches the index 3. So it gives us back Paris 2010 2.244. So this is a way that you can get rows of data out of your Pandas DataFrames. But the reason it's made a little bit more difficult than getting the column out is due to the way that the stuff's laid out in memory, effectively. It has to ask more and more difficult questions and do more work in order to extract a row than it does to extract the column. You can think columns are pre-prepared, but rows it has to go and find the data and reassemble it into a series. So getting rows out is possible. It is slightly slower. Sorry, it wasn't slow, but it was slightly slower, and that's why they make it a little bit more difficult to get access to. We can also add new columns. So here we have census, and we have a look at that table. It looks like this. So we can add a new column to it. For example, a column called continental. Again, spelling catching me out. And we can assign a value to it. So this is going to make a new column with that name. And so the value we assign to it needs to be a list of numbers to fill the column with. The easiest way to get a list of values to fill the column with is to generate one from one of the other columns. So for example, let's put some spaces there to make it clear what's going on. df city is not equal to London. So this is going to ask of the city column where it is not equal to London. That's going to give us back a list of trues and falses. We're going to take that list of trues and falses and make a new column out of it. It's not called df, is it? It's called census. Thank you. There we go. So now we look underneath and we print the census table, and there's now a new column here which has got our information in it. And we could then use this in queries as we go forwards. To delete that, we can use the del keyword, which is valid Python in many contexts, but is very uncommonly used. And you can delete a column, such that when we then look at it again, census, it is now gone. So you can add and delete columns at will. Have a go at the exercise at the bottom of the DataFrames chapter. So do this same thing that I've just been doing there. Have a go at selecting some data out of it, and then see if you can find all of the cities which have a population smaller than 2.6 million. At this point, I should point out that I've done a very, very bad scientist thing, and I've got a column here with numbers in, and I never told you what units they are in. I assume you can work out they're not individuals, because you can't have 2.148 of a person. They are, in fact, in millions. So when it says smaller than 2.6 million, it's asking for a value that's smaller than 2.6. Have a go at those for a few minutes, and then I'll update everyone before we jump onto the break. So I want to go through the answer to one of the exercises there. So the bottom of this page, this middle exercise here, select the data for the year 2001. We'll see how to do that first. and the question, which city had the smallest population that year? Now, to answer the second part of the question does require a function that you haven't been taught yet, so I'm going to teach it to you now and show how we can do this and build it up stage by stage. As Crystal was saying in the chat, the best way to solve these things is to start small, do one small bit at a time, and slowly build up your line. Because even a line of code like this one can be a little bit hard to parse when you're first looking at it. So either build it up part by part, or give temporary variable names to each step and then use those variable names in later steps. But let's get to the exercise. We have, let's make sure I've got my thing here. So we have df year. That is, oh no, it's census, isn't it? Teach me for reading off my notes. Census year. These are all the years. The first thing we want to do is grab all the stuff for the year 2001. We can do that by selecting where the year is equal to 2001, trues and falses. So let's pass that back into the census dictionary, census data frame. So this is going to give us back all the bits from census where the census year column is equal to 2001. There we go. We've reduced our data down. Now, the question in the exercise was, which city had the smallest population that year? So if you just looked at this and said Paris by reading the numbers, that's a successful way to answer the question. I can't fault you for doing it that way. But bear in mind, you could be dealing with much larger tables, or it might be running from data which is streaming in live, and so you can't look at it manually. So let's look at how we would do this using Pandas to do it for us. The first thing to look at is we've got this information here. The next question we want to ask is, what data in the population column is the smallest? Well, let's start off by getting the population column. That's given us just the data out of that column with row 0, 4 and 8. Notice it hasn't renumbered the indices, it's maintained their original numbers from the original table, 0, 4 and 8. And what we can do is take this and assign it to a new variable, because I don't want this line to get too complicated. So I'm going to call this pop, and we've got a variable called pop, which is the same thing, but it means we're always able to refer back to this set of data. If we look at pop, let's get rid of that highlighting, we could do min. Calling min on a series gives us back the smallest value in there, so 2.148. We could use that number and then refer back to the table and find the column, so we'd find the row which has that population value inside it. But that's a manual process, and we want to use the computer to do our job for us. So there's a function built into it, and this is the one I didn't tell you about, called idxmin, which stands for index min, i.e. give me the index of the row which has the minimum in it. In our case, the minimum is this, and so the row, the index of the row is 0. So this should return us 0. If we change this to index max, we see we should get 4. And we do. But we don't want max, we want min. So given that, we now want to use the fact that we know which row had the smallest population in the year 2001 by going to our census table, grabbing the city column, because we want to get the city out at the end of it all. Actually, no, let's do it the other way around. Let's do this. No, let's do city column first. City, which gives us back the city column. And then that's a series, so we can ask a question of the series by chaining together these square brackets and put inside there this question we asked. This is 0, so it's going to get the 0th row from the column here. We run that and it prints out Paris. So that is how we answer this question. Remembering that pop is actually this thing here. So if we wanted to, we could copy that. We could use our thing here, replace pop with it, get rid of these spaces, and run that. And we should get the same answer. We do. And when you look at that line of code there, you realize why I split this onto multiple lines with multiple variable names, because while this answered the question, it's a very dense and difficult way of understanding it. We've got just over an hour left today, so we've got two main topics I want to get through still. The first of which I'll jump into now, and we want to make sure we get round to making plots before the end of the session, because for a lot of you, that's going to be the reason that you came. So, I've made a new notebook here, still got my old ones open so we can refer back to them. But we're going to start off, let me just get my notes up. We're going to start off going through how we go about reading a file. So switching back to the notes. Pandas has built into it lots and lots of ways of reading files from either from your local hard disk or even downloading them directly from the internet. It's got a variety of tools for different file formats. One of the most common you're going to see is comma-separated values, CSV files. But I would not be surprised if many of you are also dealing with Excel spreadsheets. In some domains, you'll also come across file types such as HTF5 or even SQL or SQL databases too. Beyond that, there are a number of other file formats which Pandas supports, but those in my experience are by far the most common. To show how Pandas gives us the ability to read in these different data formats and to deal with the inevitable messiness that comes with them, we're going to go through an example now. In my experience, files that you're reading in are never quite in the format you want them to be. You might wish that they were perfectly laid out, neat, everything there, nothing missing. But realistically, the real world gets in the way and we have data which is messy. Either it's poorly presented, poorly laid out, or just has stuff missing from it. So if you've already come onto this page, we had to update the page in the break because something had changed and it wasn't working anymore. So make sure you refresh this page before you carry on copying the examples. So I'll refresh that now to make sure mine's refreshed. There we go, refreshed. So here is a CSV file example. It's available at this link here. So this here is the contents of that file. It's got some text at the top which describes what's going into the file and sort of an explanation about what's inside it. Then it's got the actual table of data itself. You'll notice it's using semicolons instead of commas to delineate the different columns in the table. It says up here a -1 signifies a missing value. So we've got some -1s, which mean there's no census data for that year. There's also some places where we've just got two semicolons next to each other. And that's meaning that in this gap here, there's again missing data. So there's lots of missing data. It's in a strange format. It's got some stuff at the top we're going to have to deal with. And I'm going to go through now how we can deal with this stuff and how we can get Pandas to read it in a nice way. So we start off by importing Pandas. There is a convention that when you import Pandas, you import it as PD. It doesn't matter. You could do all this just with import Pandas. But when you come to finding examples online, you'll see people using PD dot something quite a lot, so it's worth getting used to seeing that. Make sure that's imported. So the function that we're going to be using today is something called pd.read_CSV. There's a whole bunch of read_somethings. In fact, let's just have a quick look at them. This is just loading up. Read CSV, FWF, JSON, HTML, etc., etc. I won't read all of them out, but there's a lot, as you can see. The nice thing that Jupyter Notebooks give us is that if we've got a function and we don't know how to use it, we can just use a question mark and then run that cell, and it's going to print out the documentation for it. And you see here the documentation for read CSV is long. This is an example of what might be considered a bad function because it's got far too many arguments to it. But it's one of those situations where they've tried to find the balance between functionality and usability. On the whole, I think they found it correctly, but there are a lot of arguments. These are just the arguments in their default values. Scroll down further, and it has a description of each and every argument in there. So we're going to be referring back to this along the way so that we can see what we need to do. To that end, I'm actually going to switch back to the notes here, and there is a link after import pandas pd to the manual. So I'm going to click on that link, and this is that same thing but on the web page because it's going to be easier for us to search through it on the web page. So the first thing we do is pass in the file that we want to read. Now I've prepared a file for you at a link which I'm going to copy and paste there. Again, this is in the notes. This is just defining a string. We are going to pass that string to the read CSV function. And there we have it. It has downloaded the file, opened it as a CSV file, and has attempted to interpret everything that's inside it. As you can see, it's done a job, but it hasn't done a brilliant job. It is naively assuming that everything in there is a CSV file, and is asking for us to explain anything that is outside of that loose convention. So the first thing we'll see is it's included the comments at the top, all that stuff that was explaining what was inside the file. I'm going to reorganize this. You can do this in Python. You can have a function call with arguments, one on each line. And I'm going to have to use another argument to this function, tell it that it should skip some of the rows. So I'm going to go to the documentation, and I'm going to do Control F and search for skip. Now, skip initial space. Let's do match, highlight all. Skip rows. That sounds like the one we want. So let's look for skip rows. Skip rows, and go down the page. And here is the documentation for that argument. It says the line numbers to skip. That's what we want. We want to tell it how many line numbers we want to skip. So let's go back to here and pass in skip rows equals, and I think it is 5 we want to skip because there were three comment lines, then 2 blank lines. If we run that, there we go. Those comments at the top have disappeared, and already it's looking a little bit better. We've just got the data left over. The next thing is that this CSV, again in inverted commas, isn't using commas to separate the values, it's using semicolons, because I was trying to be deliberately obtuse when I designed this file so that we could learn together. So again, we go back to the documentation and go to the top, and we want to find out how to tell it which thing it should use to separate the columns. So let's just start looking for sep. There we go, sep. There's an argument called sep, which if we go down to, delimiter to use. Now, delimiter means the thing you use to separate stuff. If it's none, it tries to guess what it is, and it assumes that it's a comma. And you see here the default is it's the comma. So let's do sep equals, and then it's a string. It's a semicolon we want to use as. And so now we run this, and there we go. We're basically there. So we've had to tell it what file, what to skip, and how to separate it, and it's pretty much done the right job. You'll see in those places where we had those consecutive semicolons, we've now got nans showing up because there is missing data. They are not numbers. They're not 0. Population of 0 is a valid population. These are not values. However, you will see that there are these -1s in there. And if you remember from the documentation that we had at the top of the file, it said a -1 signifies a missing value. You'll notice partly that it's changed it into -1.000. Again, because of the whole nan thing, it's converting them all into the same data format. But we want to tell it that -1 is not a valid number. It is in fact actually signifying missing data. So there we can write, let's have a look through. Let's have a little browse at the top. This is generally the way that I work when I'm using a library. I sit here and I stare at this and see if I can work out what's going on. So let's try searching for nan. Nan. NA they're using here. Okay, so NA filter true NA values. Let's have a look at NA values and scroll down the page. Additional strings to recognize as nan. Okay, so we give it a list of strings and it's going to use them as nan values. NA values equals -1. And now we should see these -1s turn into nans. Let's watch that happen. 3, 2, 1, bam. There we go. It's now representing all the missing data as nans. The last thing we might want to do is that here we have 3 columns which contain data. Some of them missing, some of them aren't. But we have a column here which is unique. And in a census, you would normally use the year as the primary index by which to say which year you care about. You say the first thing you talk about is which year you're talking in. We haven't told it what index to apply to our data frame, and so it's generated the 0, 1, 2, 3 defaults. However, we can tell it that it should use this column as the index, and so it will take these numbers and use them as the index and have it not as a column of its own. And we do that by passing in the index col argument. We switch to the documentation, index col, columns to use as the row labels. That's exactly what we want to do. Equals year. When we run that, we see the year has become bolded, it's now down there, and we've got our data frame all working together. And because we've done that, it means we can do something like census equals this. Census, like we did before, to get the city column. Oh, hang on, no, it's not called city anymore, is it? It's called, it's a different layout. Let's get the information for London. And you see here, it's giving us a series with the columns being the years, which means we can say something like 2001, and it gives us back the population for London in the year 2001. It lets us very easily navigate down our data. So for the exercise here, go to the bottom of the reading from file chapter, and there is a link to, and I'll just go there myself. There's a link to this DAT file. So do the same thing that I just did, but doing it over this DAT file instead. And if we look at that file, okay, it's not going to let us look inside it. That's annoying. Actually, we can have a look at where it came from on the Met Office website. Loading, loading, loading. Loading, loading, loading. That's not going to load. So in the meantime, just take that URL there and paste it into the same read CSV thing we did above, and try doing that same thing. Try just fiddling with the data, try adding in skip rows, changing the separators, things like that, and see if it starts to look how you want it to. And if you get stuck, have a look at the answer, and otherwise I'll go through you all with it in a little bit once you've had a chance to play yourself. Okay, so we've got a question in chat from Jesse. Let me just get that loaded up. So you're writing this string here and you run it and it's saying invalid syntax. And the reason that's happening is because on Windows, they use the / character to represent folder separators. However, in almost every programming language, / is used for control characters. So for example, \n is a new line. And so it's reading your string here and seeing this as \U, which I think is how you write Unicode characters, and \W is something else, etc. So one thing you could do is replace all your slashes with /, because they work fine on Windows. Otherwise, as Chris says, do an R at the beginning of it, which makes a raw string, and then that will work successfully. Okay, so I'm just going to go through the first part of the exercise there. So the first part was just to open the file and get it all read in correctly. So leaving that other stuff on the screen there, I'm just going to paste that in, and I'm going to comment out the magic bits so we can kind of build it up bit by bit. Feel free, while I'm doing this, to just carry on going through the exercise yourself. If you've done this already, you don't have to listen to me. Feel free to carry on through the other bullet points, looking at negative temperatures, etc. But for those who are interested, I'll just go through this on the screen. So we read the CSV in from that file. I've commented these out so those aren't being applied. And we look at it and it looks all wrong. All the files are in the wrong place. It's got all this extra information at the top, which we want to skip in the same way we did with everything else. So when we run it again with the skipped header, suddenly we're getting data that looks correct. Again, it's assuming that it's comma-separated values, but our table, as we saw was not comma-separated. They're separated by spaces. So we want to tell it that instead of using commas, it should use white space to separate the columns. And if we now run this, we see that it works. I'll point out one thing about this data because we are going to be using it in the next section, and in fact for the other exercises. The year column here isn't the year in which the data was measured. It is the average temperature for that year, in the same way that the October column is the average temperature in October. The final thing we have to look at, and if we look at the end of the table, this will be clearer with tail. In 2019, there's a bunch of 999s at the end. And that's because I downloaded this file and put it on the website in October 2019, about 6 months ago. And so there's obviously no temperature data for the future from their perspective. Now, it tells us in the format on the Met Office website that -99.9 and -99.99 both represent missing data, in the same one that our -1 did before. And so we can use the NA values to set them to nans. So when we run this, we see the nans showing up at the bottom. That last bit there is very easy to miss. It's also very easy to miss the difference between with 1 9 in the decimal place and with 2 9s in the decimal place. Yes, there's a question there about whether delim whitespace is the same as /s plus. It's a very good question. And in fact, I can answer it by going to the documentation and looking for delim white space, and it says right here, equivalent to setting sep is equal to /s plus. Now this, for those who haven't come across it, is called a regular expression. These are very powerful ways of matching patterns, which we don't cover in this course. If you are experienced with them, you'll recognise what this means. In essence, it means a bunch of white space. But to avoid people needing to know regular expressions, they've added in the delim white space argument to make that easier for people. Bo asks, how can I set all negative values as nan? So I don't believe there's a built-in way to do that using NA values, unless you only have a subset, a strict set of negative values you're dealing with. The way that I would deal with that is to read the data in and then do a second pass where I loop over that column or apply a function to that column which replaces any negative numbers with nans. So there's a function called apply, which applies a function you give it to every row, every item in a series, and you could do a if statement inside that function which would check things out, which would compare it to 0 and then return none if it was less than 0. So I would do it as a second step after the reading in. I don't think read CSV has got built-in functionality. You could argue that read CSV has got enough arguments already without adding in any more. Yeah, exactly, as Christopher's done there. So I'll see if I can demonstrate that. So let's get rid of the NA values one here, and it just has these 999s. And if we, on the row below, do df, where df is less than 0, is equal to none. So that's going to find all the places where the df is less than 0, and it's going to set them to be none. So when we run that, and then look at df.tail, let's see if this worked. Christopher's reputation's on the line. It did indeed work. So I would do that as a second step. Okay, so I assume that people have managed to read in that data file using the example in the notes, and I should point out again, I don't know if I have pointed it out yet. On every exercise, there is almost always, I think always, an answer link. If you click on that, it will take you to the answer, where this is the lines of code that I just copied and pasted from. So if there's ever an exercise you're stuck on, you can always find out the answer and get a little bit of help. But do try and have a go yourself with these things first. So I'm going to have a look at these other two exercises here. How many years had a negative average temperature in January, and what was the average temperature in June over the years in the data set? So there's a few kind of slightly more complex questions we might want to ask there, but the sort of thing that if you're doing meteorological data are the kind of questions you might want to be asking. So the first thing there was how many years had a negative temperature in January? So we've got our DF, which again shouldn't be called DF because that's a bad name. It should be called temperatures, but let's just carry on for now. Let's start by looking at January because that's the month that we care about. That's the column. If we ask a numerical mathematical question of that or a logical question of that, it's going to give us back another series. So we can say where Jan is less than 0, that's going to give us all of our negative values. You see it's done falses. It's done a ... in the middle because that jumps from 1663 to 2015. There's several centuries of weather in the middle. Some of them are going to have an average January of less than 0, but for some reason the first 5 and the last 5 don't. We take these trues and falses and we pass it back into DF. And that's filtered down our data, so we see that all of these first column here values should all be negative. So 1684, 1695, 1709, etc. all have negative values. If we want to find out how many there are in here, the easiest way to do it is to call the len function on the list. No, my computer's having troubles. There we go. So I've just passed this data frame into len. No, I need to... That gives a different answer in my notes. Because I've got an extra pair of square brackets there that I put in accidentally. There we go. So dfjan is less than 0. df of that, there we go, is 20. So there are 20 rows which have an average January temperature of less than 0. I think there is also another way of doing it, which I'm going to try and work out live with you all in front of me, which is always a risk when you're programming. There's a bunch of functions you can call on data frames. So the result of this whole thing here is that it's a data frame. So there is, for example, I think it's summary. No, not summary. Count. This is where I should look at the documentation, but I'm being the wrong kind of lazy. So there we go, call count on a data frame. It tells you for each column how many items are inside it. I think by default it doesn't count nans, but it will count anything that's not a nan. So here's another way we could have done it. We could have said data frame of January dot count. Or if we wanted to, we could have taken from our data frame, we could have grabbed just the January values, and then we could have called dot count on that, which would have given us 20 as well. There is, as they say, more than one way to skin a cat. I don't like skinning cats at all, but if you're going to, you can do it with code. The other question that was in the notes, which I'll just move down for, was what was the average temperature in June over all of the years in the dataset? So again, average temperature in June, thing to start with is looking at the June column. Here's a bunch of data. If you want to find the average of a series, because remember when you get a column out of a data frame, it gives you a series, there's a function called mean, which you just call directly on the series, and it returns you the single value of the mean, 14. So over the last several decades, in some measurement location in the UK, which is where this temperature data was collected, the average June temperature, or the average of the averages, I should say, is 14 point something degrees. If we look at the Jan temperature, we see the average Jan temperature is 3. This tells us we are probably in the northern hemisphere. Yes, question there about why the first example I did up here didn't work. I think it's because I accidentally missed off df there when I was typing and overwrote it. So it was giving us the length of this list, which is a list of length 1, and so it was just giving us 20. We could actually, I think, have not do that at all. And that gives us, okay, that gives us all of the trues and falses, which is 361. So we want to be able to select just the data from it that is has the true value, which is those that are matching this predicate, 20. So there's a question there, how do you set the index column if it doesn't have a name? That's a good question. So the data we were dealing with here actually had its first column, the one that had the dates inside it, didn't have a name. I'll just see if I can... I don't think I have the original file anymore. Let's have a look. This is a peek behind the curtain at the material. One thing I didn't point out earlier is that the website you're reading for the notes, everything on there was written using Jupyter Notebooks. So these are actually notebook files which get compiled into HTML and presented to you. But let's have a look at the file that we're dealing with. This one here. So you'll see here, this first column here with the numbers in doesn't have a column title. And so Pandas has taken a guess and has decided that this must therefore be used as the index. That makes sense. And so it's decided to use it as the index. If you have a column in there which doesn't have a label, then what I would normally do is explicitly tell it what the label should be. So instead of it having read the file for the labels, I would say, give these the names, year of measurement, January, February, March, etc., 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 year or average. Then once that's done, I would use the labeled that I've now given it a label as a thing I pass to the setIndex function to say use this column as the index. So I do it again in kind of 2 stages. So Jesse, your question about you've got a list there, can you use a mask expression to find values? I don't think so. I'm often wrong. So let's have a look at the documentation. Actually, do I have it open already? No, I don't. And let's have a look at NA values. I did skip over it earlier. So NA values takes a scalar, like just a number, a string, a list-like, or a dictionary, and it is optional. By default, it's this. So there's no option here for the type of this to be a function. So there's no ability here to pass in something which is either a function or something which maps something. So built in, there's no ability to do that. So I would suggest using the feature that Christopher found for us earlier, where we did, commented that out, and then we did, no, sorry, we did df df less than 0 equals none. But instead of doing df less than 0, you could do some other predicate inside there. So back to the notes here. Been through these exercises. We've opened and read this separate file. Make sure you keep that bit of code around because we're going to be using it in the next section. We have done some questions on the data. We've asked about negative annual temperatures and the average temperature in certain months. And this is the useful kind of things you do. So obviously in this course, we can't get fully into depth about doing every single type of analysis. We have another course which will be running a few times after Easter, so in the next month or two, called Applied Data Analysis in Python. And there we actually learn some analytical techniques for studying more complicated things about your data. But a lot of the time you just want to do relatively simple filtering, and that's what we're doing in these sections here. The other thing that you often want to do with your data is not to look at it in a form that looks like this. I mean, it's nice to be able to look at your data in a table, but really you want to be able to see a better visual way of representing it. So for example, here we see we've got 11s and we've got 13s and we've got other things happening. It's hard to see trends in a table because you can't see anything really happening. You can see a bit of a trend. So if you look at the July temperatures, they slightly go up, they're 13s up to 16s. You know, there's maybe a trend there, but it's hard to see in a picture. So we are going to move on to the next section, which is plotting. Got just over half an hour left, which is perfectly on time. Moving on to the next section, which is the matplotlib URL, plotting data with matplotlib. Matplotlib is the de facto default plotting library for Python. If people could just post in the chat whether they've used matplotlib before or not, that would be an interesting kind of sample to get a sense of where people are. Yeah, so there's a lot more people saying yes, they've used it. I mean, I wouldn't expect everyone to have by any stretch, but it's hard to avoid using matplotlib if you've ever done anything sciencey in Python. Now, what I'm going to show you in this first section here, while it uses matplotlib, you don't actually need to know any matplotlib at all. It's a very shortcutty way of doing things, because Pandas has built into it an interface to matplotlib, which does all of this stuff for you. So let's have a go at doing some of this stuff. So I'm going to leave my df here, which is our weather data. The simplest way to plot something is to take something like a data frame and do a dot afterwards, type 4 letters, 2 brackets, and then run the cell. And at its core, that's everything you have to do. One of the things I really love about Pandas is they've optimized it for the most common use cases. It's very common that you want to just draw all of your data and just have a look at it. And looking at this plot here, can any of you see anything wrong with it? Post in the chat if you can see what's funny about this plot. Yeah, exactly, David. The y-axis is going down to -100, yet if we look at our table, we see that all of our numbers are... Oh, hang on. Looks like I made a mistake. When I was playing around and showing you the examples, I accidentally forgot to change it back so that these -99s weren't in there. And this really illustrates one of the brilliant reasons to use plotting. It's not just for having something to put inside your paper you can publish at the end of the day. It's so you have something which can visualize the shape of your data very quickly and easily. So looking through this table, we might have seen these -99s because they're at the end, but if they happen to be in the elided section in the middle, there's no way we would ever have noticed them without doing a plot. So doing a plot immediately draws on the screen. We see the green down here behind the legend. You can just about see the line going down all the way to -99.9. So what we want to do is go back to our reading function, which is further up the page. Where is it? Here it is. Make sure we've uncommented out this bit here because I was doing a demonstration. Run that, and then have another look at df. We see that df is now nan. It's the Batman. And when we plot it now, we see our data, while not pretty, is now at least laid out with the correct values. So the next thing you would usually want to do when you're plotting something is not plot all of your columns all in one big plot. You'd want to kind of pull out some kind of particular piece of information. And so instead of doing df.plot, we can instead do df year. Oh, sorry, I forgot the quotes. So df year, that is our series. And if you do plot on a series, this one here is plotting a data frame. This one here will plot a series. We get just that set of data. We get a plot of that time series. And this is where you see the very sad fact right in front of your eyes from publicly accessible information that definitely, on average, over the last 400 years, the temperature of this part of the UK at least has been increasing. There's a certain trend of, I don't know, looks like 1 or 2 degrees, which is fairly significant when it comes to the mass of air in the atmosphere. So this, I think, is a really nice way of seeing actually global warming happening right in front of your eyes. Now, a plot by itself like that is nice. We can see our data and it's good for exploring things. But you usually want to actually do something to your data. You want to be able to label it and give some information to your reader. And so the way we do that is we say, we take the result of this df year plot thing, which as it happens is the thing that's being printed out here. It's a matplotlib thing. And let's give it a name so we can refer to it later. So year plot, run that again. Same thing happens, but now it's been stored inside this variable. And because we've stored it in that variable, we can do things to it. We can say year plot dot set y label is temperature. And then we run that, we'll get a y label appear on the left hand side. Oh, I can't spell, thank you. Year plot, there we go. Now that's all showing up how we want it to. And temperature is showing up on the left hand side. Now in the notes you might notice I've got some weird stuff going on, where after temperature I've written $$ circumflex / circ C and written an R at the beginning. And this bit in here, if any of you have used LaTeX or tech before, it's a way of representing sort of mathematical symbols. This means superscript, draw a circle, so that's going to do a small superscript circle, and the letter C. The R here is needed for that same reason I said earlier, so the backslash isn't interpreted by Python. So when we run this, we get, oh, the brackets are in the wrong place. There we go. We get degrees C, so you should always have your units on there. So have a go at that yourself, reading the data, plotting the thing. The exercises are further down the page, just above halfway, about a third of the way down. Reproduce that plot, try tweaking the labels, try putting the X label on, see if you can guess what the function is to set the X label. Try plotting some different months, and then we'll move on to the next little bit. So David, as to your question about what kind of object R is, everyone else can just carry on for the minute, you don't need to listen to this. I'll demonstrate. In summary, it is the same thing. So if we look at type, no, if I could spell I would, type of hello, it is a string. If I look at the type of R hello, it is also a string. So the way that Python uses this R in front of it is it kind of uses it to pre-process what's literally written here before it turns it into a string. Normally Python reads a quote and it happily plods along until it sees another quote, and it does stuff to things in between like new lines. What the R here does is it changes the way that it reads through this string before making a string out of it. And what the R really means is don't do anything until you see another closing quote. Adam, to your question about square brackets and round brackets, as Christopher says, exactly right, square brackets are used for indexing and round brackets are used to call functions. When it comes to things like pandas, it's a little bit more complex than that. It's completely true that that's what it does, but I tend to think of it more about square brackets are used to ask queries of the data, because you can do more than just ask for a single index. You can pass in, for example, that series of trues and falses. So because you can put more complex things in there, I think of it more as a query syntax, where lists and dictionaries have got a very simple syntax, but series and data frames have got a more complicated query syntax. But as per the language, square brackets means index operation. And the next little section is other kinds of plots. So you might have noticed we never specified what kind of plot we wanted. Pandas just defaults to, if it's .plot and you're doing it over a series, or a data frame which is just a bunch of series, to do a time series plot effectively. It treats it like that. Now, different kinds of plots actually need different kinds of data. And this is something that I think when you're taught about bar charts and histograms and stuff at school, it isn't always quite made explicit. But I see a lot of people making mistakes by just thinking, I've got some data and I want to represent it in this way. And maybe the two of them don't actually make sense together. For example, you shouldn't just, or you could, but maybe it wouldn't make sense, just take all your data here and plot it as a bar chart. Because arguably it's continuous data. Maybe it's continuous, maybe it's not. That's really where it starts to get a bit blurry. But for example, if we wanted to do a chart of the temperature in each decade kind of could be thought of as a independent singular value, and so we want to plot a bar chart of the temperature in each decade going across the sheet. So let's have a little look at how we can do bar charts. So at its most simple, I will do the thing I just said I wasn't going to, and show you that you can do .plot, and then before doing the brackets there, you can write bar.plot.bar and then call that as a function. It's a bit of a weird syntax for people who are used to Python, but there is a way to make this work. You run that, and it does a very, very, very dense bar chart, where everything's smashed together and you can't really see very well what's going on. Now, that's not a very useful thing to do. Really, we want to look at a sort of a simplified view of this. Here we've got 300 or 400 pieces of data. Bar charts don't work well with that many pieces of data, so we want to simplify this down. So let's delete that cell and start again. So I'm going to introduce, while I'm technically introducing bar charts, I'm going to introduce a few other bits of syntax in here which I think are useful things to know about. So first of all, we've got our data frame. If we want to get out just the years from this data frame, the years here are in the index column. They're not a column by itself, so we can't just do square brackets index because there's not a column called index. Instead, there's a shortcut which gives us the index, which is just .index. That gives us back, effectively, a list of all of the index values. What we want to do to turn this column here and group these by decade is to have our table here. And the way we're going to do it is we're going to make a new column on the right-hand side, which has inside it the decade that each row is in. This first one will say 1650, 1660, 1660, 1660, and so on, up to 2010, 2010, 2010, all the way to 2019, being also 2010. And to do that, we're going to do a little bit of string manipulation, and so I'm going to sort of play along with this, and if people have any questions along the way, ask in the chat, and I'll try and pay attention to both windows at once, but otherwise I'm sure my helpers will keep up. So we're going to make a new series which contains this column here, but turned into a string. So df.index, and we're going to turn that into a series. We're turning it into a series so that we can add it as a new column. Now the index of that new series has to match the one we're going to insert it into, so it has to use this same index here. So this is very repetitive, but df.index. And if we look at that, I forgot to import pandas on the screen. From pandas import series. Here we have index column, values column. They are the same as each other, and the d type is integer. However, we want to have these as strings because we're going to be doing string-like things to them in a moment. So we apply to the data in that column the string function. Looks the same, but now the d type has changed to object. And this we are going to call years because these are the years that we're dealing with. We're going to take that and we are going to apply another function to it. And the way we're going to apply this function is something you might not have come across, and that is a lambda function, which is a way of very concisely applying a bit of information to something. So this x here is going to represent each year, each row from our series. And so we're going to take each row, and that is going to be a string, which is 4 characters long, like 1659, for example, or 2019. And we are going to take the first 3 characters from it, and then add the string 0. So we're cutting off the units number from the year and replacing it with a 0. And if we look at that, we end up with 1650, 1660, 1660, so on, 2010, 2010, 2010, 2010. So this is now our data which represents the decade that we're in. We can then go back to our data frame. And assign that series we've just created with the decade strings to the decade column. So it's going to make a new column called decade. And so now when we look at df.head, we see we have a new column decade which has 1650, 1660, 1660, and so on and so on. So in order to plot our data by decade, we first had to make a column which represents a sort of a consistent piece of information for each row that we want to group together. Because the next thing we want to do to our data, a thing you can do in Pandas, which we haven't come through yet, but I'm going to introduce now, is grouping. So if you have a table of data, you can group together rows based on certain conditions. In the example earlier, we had that continental column we created based on whether the city was or was not London. So we might, for example, want to group our table we had earlier by is this continental or is it not? Then we could look for getting summary statistics for one group, summary statistics for the other, and then we can compare the two against each other. In our case here, we want to find summary statistics by grouping together based on the decade. We want to have we're going to make a new table which has one row per decade. And the row per decade is going to be made up by averaging the stuff that are in the rows that are inside said decade. Let me just switch back here. So to group things in Pandas, we do df, remember df is this table here, dot group by decade. If you just give a column name, it will group by all the values that are the same in this column here. So it will make one group which contains this one row here, 1650. It will make another group which contains all of the ones that are 1660. Another row which contains all the 1670s, 1680s, 1690s, and so on. So it'll end up with one group per decade. Then we tell it what we want to do to each group. If we just look at what we get here, you see it gives us back not a table which has the groupings in, but some kind of intermediate object. And that's done for performance reasons. But we can tell it, now what we want to do to each of those groups, we want to find the mean of each group. And when we run that, we get back this. So you see here, it's made a new data frame. This is not the same data frame as before. The index is now based on the thing that we grouped by. So the decade is now the index, because we told it to group by decade, and so it's taken that to mean decade is the important thing, so use that to index our data. It's then made a row for each decade, where the values in that row, for example, this 2.60 here, is made up by averaging all of the rows from the previous table, which are in the 1660 decade. So 0, 5, 5, 1, and then some more that are hidden down here. So that gives us 2.6. So this has given us a table which is now actually small enough to fit on the page. These are all the decades between the start and the finish. I know scrolling is difficult when it's like this. So let's change this to dot head, just the first few rows, or dot tail, the last few rows. Good, Christopher's doing a brilliant job keeping up with me in the chat. So the very last thing we want to do is assign this to give it a variable name. Let's call this by decade. I can never spell decade. So this variable here is that data frame that we just saw, by decade. So if we call dot plot on by decade, we will get a line plot over the decades, just like we did before. But you see how we've reduced the noise in the data because we've averaged over the values within each decade. We don't want to plot all of them, we want to plot just the year because we want to reduce the data we're plotting still. This is where we really see that upward trend very, very clearly. Before it was slightly lost in the noise, but now you can clearly see over the last 100 years the temperature has shot up. You could say the same thing between 1880 and 1720, so maybe they were worried as well, but we know there's a global trend now, not just a local one. To make this into a bar plot, we follow plot with dot bar, and there we have it, a bar plot over the decades. So in summary, to do a bar plot, you just follow the plot with dot bar, but you do have to think about the kind of data you're doing things to. So if you want to do group by, you need something to group it by, and then you need to call the group by function. Last thing on this pandas-driven plotting chapter I wanted to cover was saving a plot to a file, and I saw that someone in the chat already got to this point and having a go and they were having issues, so I'm going to go through it on the screen up here. I'm just going to delete that file because I don't need that one anymore. There we go. So, let's make a new cell. And let's see about how we go about saving this file. Now, in Matplotlib, like in many tools that are around, especially in programming land, there is often more than one way to do it. Now, a well-designed API will give you one clear and obvious way to do something, but it's not always possible to only have one way to do it. So I'm going to show you a way to do this. I'm sure that some of you, if you've done these things before, have alternative methods, but this is the way that I've used, and I think it's nice and reliable. Also, it has the advantage that it works outside of Jupyter Notebooks. So if you're doing your plots just in normal Python scripts, this is going to work well there as well. So we start with our df year dot plot. It plots it to the screen and we've got the thing showing up. However, it's plotted to the screen and has kind of got rid of the context that was around it. So I'm going to show you now how to explicitly specify some of the things that Matplotlib and Pandas is assuming for you. So the way that Matplotlib works is it works on these axes idea. Now an axis in Matplotlib terminology you can think of as being a plot, a single XY plot or 3D plot or something like that. Now Matplotlib also allows you to have multiple plots all on one page. The terminology it uses for that is one page which might have multiple plots in is called a figure, and then you have multiple axes within a figure. So if you want to do multiple subplots on one page, you need to start thinking in terms of figures and axes, and that's going to make your life much simpler. So the way that you'd start by doing that is calling the, well, first of all you'd have to import matplotlib dot, is it plotlib? Let me just check something. I always forget this. pyplot as PLT. So because we're going to be using Matplotlib functionality directly in a moment, rather than just Pandas interface to it, we have to explicitly import Matplotlib. Until now, Pandas has been doing that for us behind the scenes. We then call plt.subplots. This is going to return to us by default a figure which has inside it one subplot. If we want multiple subplots, we could put in 2 there, and we get a figure with 2 subplots, or 2 axes. By default, it just gives us 1. We give them names, it returns us 2 pieces of information. It gives us the figure and the axis object. So the figure is the page, axis is a plot that we can start to draw on. By default, this plot here is empty, there's nothing inside it. We want to plot our data into this axis, which is inside this figure. And we do that by passing the ax argument to the plot function equals ax. So if we run this again, it should look exactly the same as how it did. What happened there? Subplots, sorry, it's plural. There we go, exactly how it did before. If we change that to 2, it's going to complain because we are getting back 1 axis object, but we're asking for 2. But we can do that if you unpack the arguments. Once we've got this, we can then refer to this figure object, which knows about everything that's inside it. And so we can end the line with fig.savefig, and we give it a name, my plot.png, let's say. And it's going to save that. And you see, as I press that, my plot.png appeared over here on the left. Let's prove that happened by deleting it and running that cell again. It appears over here. We can open it up and we see this is the plot. In Markdown mode, we can code Markdown. We can then display that plot by using the Markdown syntax for showing a picture, which is my plot.png, and then it shows up in Markdown mode. This is a picture, so we can have hello, bye in front of and behind it. So that's how you save figures. And if you have your analysis pipeline from reading in your file, doing your analysis, all the way through to saving your figure, you can then run that anytime and update all the plots in your analysis in one go, which is a really, really nice way of working. So in the last few minutes, I'm not going to do any more code because the very last section in here, if you go to the bottom of the matplotlib chapter and press next, there's a section called Making It Prettier. So this section, again, I suggest you have a look through in your own time because there's quite a lot of very dense code. Do email us if you have any questions. But to summarize, with matplotlib, you can go from making a plot which looks like this, which is using the default colors, default axis labels, etc., until you get a plot, excuse the scrolling, that looks like this. So there we've changed the axes, we've changed the colors, we've added in labels and written mathematical texts, we've put in a legend, and it's able to present things in a nice way. So matplotlib gives you the ability to do that, but if I scroll up just a little bit, you see that the code can sometimes be a little bit complicated. So have a look at this section in your own time later on. I tend not to go through it in the class because it's just a lot of repetitive stuff. But do have a look at this, go through it step by step. It should explain what's happening along the way, and you can see how you can start to design your plots to be a little bit better presented. Moving on to the summary now. That's everything I wanted to talk about in the course, basically. So thank you all for coming along today, and I'll hopefully see you again in a course in the future. Welcome to Applied Data Analysis in Python. This is a course which follows on from our Introduction to Data Analysis in Python course. That previous course introduced the basic tools that Python provides through Pandas to read in data, query data, and interact and select subsets of your data, and finally plot any information you've extracted. The purpose of this course is to take the next step and discover some more advanced tools you can use to start from data and extract information from it. More complex queries than simply, I want to get all the rows that match this label, but more advanced, intricate data analysis tasks. We could name this course Machine Learning in Python, since that's effectively what we're going to be covering. But machine learning is such an overloaded term that I think thinking about what you're doing to your data to get your questions answered, rather than necessarily the umbrella of the tools that you're using, is sometimes a slightly better way to think about how you're doing things. So I'm going to start by moving to the next page in the notes. So, as I said, we're mostly going to be learning about machine learning techniques today, or at least some things which fall under the umbrella of machine learning. Now, machine learning is a slightly overloaded term. I'm going to try to, throughout the course today, explain what machine learning is, how it fits in the context of wider topics such as AI, and how some of the techniques specifically we're using can be used, and why machine learning is more appropriate description for them than just statistics. Machine learning covers a whole host of tools. You might have heard of neural networks and deep learning and things like that. Those are techniques which use machine learning to discover information about data. At the very other end of the scale, perhaps the simplest form of machine learning that I can think of is the linear fit or linear regression. So that is just taking an X and a Y axis, a scatter plot, and plotting a line of best fit through your data. That is going to use machine learning techniques when you do it on a computer in order to get the information. And that really gets to the crux of what machine learning means. It is simply a statistical technique you apply to your data, but because you're doing it on a computer, you are using a machine, and so the machine is the thing that is doing the learning, rather than you sitting there with a pencil and paper and doing it by hand. So we're going to start off by launching into doing some data. So I'm going to do a little example here, and I'll pause every now and again to let you follow along and catch up. Otherwise, if you feel happy to, feel free to type as I talk. Almost everything I type is going to be coming out of the pages of the notes. So I'm going to start by loading up pandas. So from pandas import read CSV, because we are going to be downloading a file. I'm going to copy and paste this because no one wants to watch me type out a big long URL. We are loading a CSV file. It's downloaded it. Let's have a little look at the top of that file. It is a CSV file, which if you had a look at it, you'd see it's 2 columns of text separated by commas. Therefore, it's been read into pandas as a data frame, which is a table which has 2 columns. The first column is labeled X, the second column is labeled Y. We also have a row index for each of the rows. Largely, we're going to be ignoring row indices in the data today. We are just going to be selecting columns from our tables of data. This table, as I said, has got 2 columns, X and Y. And I'm going to start by trying to clarify some terminology, because the sooner you get the terminology understood, the more easily you're going to pick up more advanced terminologies and concepts as we go through. And so the first thing I want to point out is the use of X and Y in machine learning. They have the same meaning as your traditional X and Y on your scatter plot, where X goes along the bottom axis and Y goes on the upwards axis. They're usually drawn that way because X are your independent variables, the things you've measured, and Y is your dependent variable, the thing that you are trying to find out about. And the same thing happens when you're doing stuff in machine learning. It is usually the case that you collect your X data and you want to use X to predict what Y is going to be. In this table here, we have one single column of X. Though it's possible, and we'll see this in the course today, you can have as many columns of X as you want, X1, X2, X3, etc. It's usual that you only have one column Y, though in principle it's possible to have more complex data there. So at its root, what we're going to be doing with machine learning today is using X to predict what Y is. And that's exactly what we're going to do with our scatter plot here. But let's have a little look at what our data looks like. So first thing to find out is how many pieces of data we have. It's telling us the X and the Y columns both have 50 rows in. So we've got 50 data points. Once you've got a vague sense of the shape of your data, the very next thing I tend to do, and we'll be seeing more and more in this course why that's a useful thing to have, is I'm going to look at what the data looks like when plotted. So let's do data.plot.scatter X and Y. And we get here a scatter plot. You see our data is looking relatively linear, starting in the bottom left, going up to the top right, but there's a bit of scatter to it. What we want to do is, for a given value of X, predict more or less what the value of Y is. This is what a linear fit does. So I'll just give you 20 seconds or so to copy those lines of code into your notebooks, check you get a plot that looks the same as what I'm seeing, and then we can step on and start actually using some machine learning on this data. So hopefully that's all working for you. You've managed to load in the data, get the scatter plot going. So as with all data analysis tasks, we've started with our data. We've looked at the shape of it, we've looked at how it looks when plotted. We've guessed what the approximate relationship between the parameters are. We've guessed that between X and Y there's going to be a linear relationship of some kind. Once you've decided how you want to represent the relationship between your X and the Y, the next thing is to go and find some piece of code which is actually going to be able to extract the underlying parameters of that relationship for you without having to do a whole load of maths by yourself, by hand. In the course today, we're going to be using a package called scikit-learn. There's also another package called stats models. Both of these are linked in the notes. So if you have more complicated statistical things you want to look at, then stats models might be a place to look. But for most machine learning tasks, scikit-learn is going to give you a nice, easy to use interface to extract most of the information that you need. So let's start by extracting our model we want to use. So we're going to go from scikit-learn. Now we are looking at linear models here because we think there's a linear relationship between the two of them. So there is a linear model package inside the scikit-learn package, and from there, and I found this out by Googling and looking at the documentation, there is a package called linear regression. So every model that scikit-learn implements is implemented as a class. You import the class that you want to use. You then make an instance of that class. Now, at the point you make an instance of that class, it's effectively making an empty model which knows how to learn from your data, but hasn't yet learnt anything from your data. So we do something like linear regression. Linear regression is a class, and so we can call it with a pair of brackets like a constructor, and we assign that to a variable. This model object is now our model, which is ready to learn from our data, but is currently got random or empty attributes inside it. When we show our data to this model, it is going to go away and tune the various parameters that describe how the relationship works. In the case of a linear regression, the two parameters that are going to be tuned are going to be the gradient and the y-intercept in principle. More complicated models will have more parameters inside them that are going to be learnt as the model looks at your data. There are also things that you can tune on a model which you set once up front, which aren't learnt from the data, but you as a data scientist, which you are all becoming throughout the course of this afternoon, you want to set in advance. Now, the things that it learns during the process are called parameters. The things that you set up front are called hyperparameters. And there's a hyperparameter that we might want to set on our model here, which is to tell it that we do indeed want to fit the y-intercept. Some linear regression models fix the y-intercept to 0, so we want to make sure that the y-intercept is going to be fitted as part of learning about the data. So we pass in another parameter, fit intercept equals true. And then we run that cell. So if you could all run those two lines of code now, make sure that scikit-learn is working, is installed, it's able to run at least that much, then I'll step on to actually fitting the data. We've now got our model. It's sitting there ready to learn. It's like a student who's just turned up at the beginning of class, doesn't know anything yet, but knows how to learn, but just needs to be given the information to extract the things that they really, really care about. Hopefully that's how you all feel, and you will learn something throughout this course. So in order to allow the model to extract the parameters of interest, which as I said are going to be the gradient and the y-intercept of the straight line, we have to show it some data. Now, all models in scikit-learn have a nice consistent interface to them, and that's you type the name of the object that represents the model you've created, and you call the fit function on it. All models in scikit-learn have this fit function. As to the arguments that the fit function accepts, again, there's a good amount of consistency here, but it's important to understand the type of data that it expects you to pass in here. For a model like this, where we're showing it some data that we want it to learn from, and some more data we want it to learn to, i.e. the x and the y, the fit function is going to take two arguments, effectively x and y. But we can't just write x and y, we have to actually give it the data, which from above we've stored in our data object. The fit function expects the x argument to be a two-dimensional object. That is, we can't just pass it a single list of numbers, we have to pass it a table of numbers. Now we're going to get our data from our data table, which we had above, and we would, in principle, want to grab our x column from that table. The only reason we can't do that directly is that the x column from our table is only a single column, and with pandas particularly, if you extract a single column out of a table, it gives you back a one-dimensional object, basically a list of all the numbers. We want to tell pandas that we want to get a two-dimensional data frame out of our larger data frame, And so we have to tell it we want to get a data frame which is made up from the columns x. Now, in principle, if there were multiple, we would do x, x1, x2, etc. But in our case here, because our data only has one single x parameter, we just ask for a single x. And that is why we have these slightly strange looking double square brackets when we call the x parameter. That is to make sure that our x parameter being passed in is two-dimensional. It should be a table of data. One row for every sample, one column for every feature or x value. The second argument that the fit function takes is, unsurprisingly, the y data. Now, in this case, it is okay with the y data being a one-dimensional list because there is only usually one column of y data. For each sample, i.e. for each row, and I'll just scroll up, it is going to use all of the x's to work out what the y is. And then the next sample is going to find the relationship between all those x's and the y. So we're passing in our x data as a two-dimensional table and our y data as a one-dimensional list. At this point, we can go ahead and run that cell. And in that split second, it has gone and done the machine learning. It has computed some algorithm. I think it uses ordinary least squareds to calculate what the line of best fit through the data is. And it has now saved the results of that into this model object. So by calling the fit function, you have performed the machine learning step. Because we only got 50 data points and a one x value and one y value, it only takes a fraction of a second. With more complicated models, it could potentially take hours to run this single line of code if you were doing something a lot more complicated. If you could all run that line of code as well now, make sure that's working for you, and then I'll step on to the next section. The learnt parameters are now inside this model object, and this might be a case of you've got to trust me, they honestly are inside there, but you absolutely should not just blindly trust me. You should be asking the question, how can I get access to those parameters? It's all very well it having learnt about the data if we can't then extract out the stuff that it's learnt. The number one way that you get access to the data from the model is by calling the predict function. So the predict function, after the model has been fit, can then be passed in to x data and will make a prediction of what the corresponding y data should be based on the model that it's been able to create. Given that we've got a straight line, we will be able to plot a straight line of what our predictions look like simply by grabbing the upper and the lower points that we care about and then drawing a straight line between those 2 points. So let's grab our 2 points that we care about, our upper and lower bounds on the range that we're looking at. So we can get the lower bound with data, from the x column dot min. That's going to be the smallest x value, and then data from the x column dot max. Let's stick that inside a list. It's a 2-item list. And then for sake of getting things in the right shape, we want to turn this into a table of data. So I'm going to do the similar thing to what I did before, frame, where I make the x data into a data frame. I'm going to call that x fit. Because I'm now using the data frame, I've got to from pandas import data frame. The reason I've done this data frame thing here is because we're creating x data again. And the same as with the fit function, our x data had to be in a 2-dimensional table. Likewise, with the predict function, our data has got to be inside a 2-dimensional table. We can then pass that to our predict function. It's going to make a prediction once for the minimum value, give us back what the corresponding y value is, and then it's going to do it again for the max value and give us back the corresponding y value. So this will give us back 2 pieces of data, which we are going to save into y predicted. Best way to visualize things is to plot them. So let's do data.plot.scatter, exactly the same as we did before, x and y. So we're plotting our overall data there. Save that plot so that we can plot the other data on the same pair of axes. And on this second pair of axes, over the top of the scatter plot of our data points, we're going to plot a straight line with the x values x fit and the y values y predicted. I'm also going to set the line style to be a dotted line. That's how you do that in matplotlib. So now if we run this, we get our original data as we had it before, but we also get plotted a dotted line showing what the model has made a prediction of. This dotted line has been created by predicting a point down here on the bottom left and predicting another point over there on the top right, and it's drawn a straight line through the two of them on this line here. So visually, it looks like it's doing a good job of predicting what our data is. The question is, a visual representation of our data is only so useful. Often we want to be able to extract numerical values from our data. In order to do that, the data has been saved onto this model object, and so we can extract that out. So I'm going to make another cell here and have a look at some of these pieces of data. So the coefficients, which is going to be the gradient of the line, are saved in an array on the model object, which is in this case got the value, so one element array with a value of 1.977. The reason the coefficients are returned as an array is to have a consistent interface in case we were fitting over a polynomial of some kind, in which case there will be multiple coefficients here. So since we've only got one, we'll just ask for the 0th coefficient. And we can also have a look at the intercept. You'll notice that both of these attributes have got an underscore at the end. That's a scikit-learn convention used to represent attributes which only exist after the fit has been performed. So if you ask for these and you hadn't yet run fit, you get an error. The underscore tells you that this is a learnt attribute, or learnt parameter, I should say. Have a look at what the intercept is. No, I did that wrong. Have a look at what the intercept is, and it says it's minus 4.903, etc., etc. Now I expect on your computer you've got exactly the same numbers as these, and that's because this is a relatively deterministic algorithm. There isn't much randomness going on, and so since we've started with the same set of data, we run basically the same version of the fitting package, we end up with exactly the same number at the end. If you were on a different version of scikit-learn, maybe even on a different version of Python, you might end up getting slightly different results here, but they should always be the same to a certain number of decimal places. So this is telling us that we've got a line that is being represented more or less by the equation y equal to 1.977 times x minus 4.9. We look at minus 4.9, we see on the plot above that it does probably hit the y-axis at minus 5-ish, and the gradient is about a gradient of 2. So these numbers are fitting with our expectations. As it happens, this data was created from a gradient of 2 and a y-intercept of minus 5, so the slight difference here is down to the randomness that I introduced into the data. So have a go with doing that yourself. Run the same model above and try fitting it all out. The exercise that I'm showing you here is at the bottom of the fitting data chapter. All of our exercises are in these yellow boxes. So have a go at fitting that data, making sure you get the same thing above. Once you've got that working, have a go at doing the same process on a different data set. So scikit-learn comes with a bunch of example data sets, which you get through sklearn.datasets. There's one which represents diabetes patients. So try doing a line of best fit between the BMI column and the target column inside there to see if there's see what the relationship between those two parameters is. I'll give you a few minutes to have a go with that, and then we'll carry on to the next section. I'm going to go through the answer to the diabetes example now on the screen so that everyone has an example of how it's working. As with all of the exercise today, there is an answer linked in the notes, so you can always check that if you're struggling, but sometimes talking it through is a better way to learn. So down here, I'm going to make a few cells, and I'm going to paste in the bit of code that was basically given to you. Here we're calling the load diabetes function. It's giving us the data. The title, the column headings are coming from the function's feature names attribute, And we also take the target column. This represents the Y that we were talking about before, and we put that into the target column. When we look at that, we get some data that looks like this. So we've got age, sex, BMI. That's the column that we're interested in for doing our linear regression. A bunch more parameters, which are documented, but I don't know what they mean, and a target column. So the question we're asking here is, what is the relationship between the BMI column and the target column? The first thing to do there, really, is to do a fit. Now we do that using AX equals diabetes.plot.scatter BMI and target. Have a look at that and we see there's definitely a loose relationship between the two of them. It's a very wide distribution, but there's definitely some kind of relationship there. But we want to be able to extract out a numerical value which represents the two of them. So let's do that same thing we did before. Model equals linear regression. We want to make sure we're fitting the y-intercept. And then we fit our model with model.fit. Here again, we need to make sure that our x values being passed in are two-dimensional. So we do diabetes square brackets, and then we want to do a second pair of square brackets and ask for the BMI columns. As our y value, as our target we're aiming for, is our y-axis, which is going to be diabetes target. If we run that, it's going to fit the model, but we want to also plot our model. So I'm just going to copy and paste these two lines of code. They're exactly the same things we did before. We get the minimum value from the BMI column and the maximum value. We make a prediction for each, and then we are going to plot that prediction onto the same axis. Line style equals dotted line, and this time let's make the line red, make it a bit more interesting. And there we go. It's made an estimate of the relationship between those two things, and it's plotting the line. So you see here, no matter what data you've got, as long as you've got an input column and an output column, you can always extract the two of them. Sure, there's a question in the chat there, Abada, asking, can you explain why the X data should be in a 2D array? So the reason for that, and I'll get onto this in a bit more detail in the next section, is that in general, your data is going to have multiple measurements you made, and then you want to make one eventual prediction. So the example I use in the next chapter is that you're maybe trying to come up with a model which is able to predict the price of a house. And so you might want to work out what the price of a house is based on the number of rooms in the house, the size of the garden, and how many schools there are nearby. So you've got three things of interest that you've measured, and based on those three things, you want to be able to predict what the house price is. And so because in principle, your thing you're learning from can have 2, 3, 4, 1,000 different columns or features that you're looking at, the fit function in scikit-learn will always assume that your X data is going to be a set of columns. It's going to be a two-dimensional array. It's going to have a row for each sample. In this case of the diabetes, each sample is a person. In the case of the house price data, each sample is a house that you've measured the number of rooms of, the size of the garden, and the number of schools in the area. So because the fit function is always assuming this is going to be two-dimensional, even if we only have a single column of data, we have to pass in a two-dimensional object which represents even a single column. To explain how this syntax works a bit more, let's have a little look. So let's look at diabetes. Let's look at the whole thing. There we go. So that's the whole table. It is two-dimensional because it's got rows and it's got columns. A row in these tables is often called a sample or an example or a measurement. In general, each of these column headings are called a feature because they're a different feature of the data. You have an age feature and a sex feature and a BMI feature. In the table here, we've also got the target, which is, well, sometimes it's called the target, sometimes it's got other names, but in general, we're going to call it target here. If we look at the number of dimensions of this, which you can use using ndim, it tells us it's 2-dimensional. If we look at the shape of our data, we see it's 422 by 11. 1 dimension, 2 dimensions. So here we've got a 2-dimensional table of data. We want to train our model based on the BMI column. So let's have a look at what that looks like if we just extract the BMI column. It gives us back a single column of data. These are the data in this column. The numbers here are just row labels. So we have a single 1-dimensional column of data. And I can prove to you that it's 1-dimensional by copying that code, pasting it, and doing ndim. And it tells us that it is indeed 1-dimensional. We want to extract this same data here, but we want to have it represented as a 2-dimensional object because Fit always wants your data as a table with n columns. Whether n is 1 or 1,000, it wants it as a table of data. And so to do that, we do diabetes, square brackets, and instead of just doing a single object there, we can pass a list of column titles. We can pass BMI and age and sex, and when we print this, we get out a subset of that table with just those columns in. If we look at the number of dimensions, of course, it's 2-dimensional. Using this same syntax, we're passing a list in here, but we can pass in a list with only one item in, so we can delete those two things. We're still passing in a list, but it's only got one object in. But because we're passing in a list, Pandas is going to give us back a table of data at the end rather than a single column. So that gives us back a table of data in contrast to the single column of data we got here. And that is happening because of that extra pair of square brackets. If we look at the number of dimensions of this, we see that this is now 2-dimensional. So scikit-learn always wants the X data to be as a table because in principle it can have multiple features. In our case here we only have one feature, but we are still having to pass it in of the same shape of data. Most programming tools have an assumption about shapes of data and so on because it makes their internal logic easier. If we only passed in a 1-dimensional thing, it wouldn't know whether we were passing in a single column with multiple samples or a single sample with multiple features, for example. So I'm going to talk a little bit first, before we get on to other techniques, about what machine learning is, how it works, and how you can think about starting to apply it to your data. And by apply it to your data, I mean think about what it's possible to do with it, so you know what questions you can ask of it, so you can plan right from the beginning to use machine learning in your analysis by making sure you've collected your data in the right kind of format. But on the whole, there are two main classes of machine learning. We have supervised methods and we have unsupervised methods. Now, a supervised method of machine learning is one where you've got a set of features, a set of x's, and you want to, based on the values of those features, predict what the value of a target is going to be, what the value of y is going to be. So a supervised model is one where you're finding a relationship between x and y. You're trying to learn out how to get from one to the other. Remember that x can be multiple different features, so you're trying to see how to get from those data to the y target data. So that's what a supervised model is. Now you can see the linear regression we were doing in the last section was one of those. It was a supervised model. We were trying to find the relationship between our x column and our y column. Similarly with the BMI example, we were finding the relationship between BMI and target. Within supervised techniques, there are two main categories. Those fall into classification and regression. So a regression is what we were finding with our linear regression, hence the name, just there. Our target was a continuous value. Based on our inputs, we were trying to find out where on this scale our estimate was going to end up. With the house prices, that's a regression example because we are trying to guess what the price of this house is going to be. From £0 up to £1 billion, it's somewhere on that scale. That's the range of value we want to predict that we want to end up inside. By contrast, some supervised techniques are going to do what's called a classification. They're going to take the set of features, the set of inputs, and it's going to put them into one of a set number of buckets. For example, you might be trying to work out what species a particular kind of flower is. You take some measurements of it, and at the end of the day, you're not going to find out how much of one species or another it is. It is going to be falling into species A, species B, or species C, for example. So they're both starting with some features and trying to end up at some kind of target, but whether that target is quantized or continuous tells you whether you're doing a classification or a regression. So the thing we did in the last section was a supervised regression. Most of the time when people think about machine learning, they are talking about supervised methods. They are talking about these kinds of things where you're finding a relationship between your inputs and your outputs. If you're doing a technique where you're trying to take a picture of an animal and tell you if it's a cat or a dog, that's a classification. If you're trying to take some features about a person and trying to work out whether they should have a loan because they're going to be likely to or not pay back the loan, that could be a regression because it's giving you back a probability which you're going to interpret. The other major class of machine learning is what's called unsupervised. Unsurprisingly, given the other one was called supervised. Now, an unsupervised machine learning model is one which doesn't have a target. You have all your features, you've got all your x values, but you don't have a y. You're not trying to get to a particular place. You are just trying to understand some internal relationship between all of the features that you're putting in. It can be a little bit hard to understand how it can possibly learn anything if it doesn't know where it's supposed to end up. But depending on the kind of question you're asking, there are things that you can extract about your data. The two main classes here are clustering, where you're trying to find subsets of your population of samples and put them into buckets. It's kind of like a classification, but where it's working out its own categories. Or things like dimensionality reduction, where it just looks at your data and it tries to just simplify it in some way. So it's not trying to get to a particular place, it's just trying to reduce down the amount of information you have to think about. So these techniques are often used in concert. You might do a clustering before you do a classification or something like this. They're not, you don't just use one technique and call it done. You often have combinations of these things. But if there's no question on that first section there, then I'm just going to talk through now the process that you go through for supervised learning. Because supervised learning, as I said, is one of the most common techniques that get used. And it's often what you end up doing in your research or scientific contexts. You've made some measurements and you want to make a prediction because you don't want to have to run the real experiment every time because experiments are expensive and difficult, or maybe they can't be run because they were time-based in some way. So you want to make some kind of computer model which is going to represent what you think is happening in that experiment. So the supervised learning process is a fairly standard set of steps that you'll go through, and it all starts with collecting your data. Well, I suppose it starts with deciding the question you want to answer. Let's say, as I was mentioning before, that we want to have an example where we are predicting the price of a house. We want to measure how old the house is, how many rooms it's got, and the size of its garden. Those are all things which are easily measurable. Anyone can count how many rooms a house has, measure its garden, and look up on some records how old it is. But it does take an expert, or it takes the market, to work out how expensive a house is going to be. And it is a question you want to answer before you go into the process of trying to sell your house. You want to make sure you're going to get your money's worth for it. So in order to work out a model which is going to relate the price of a house with those features of it, we need to go out and collect some data to train a model on. So the first step here is to go out into the wild and find some real houses, measure their features, measure their ages, number of rooms, size of gardens, etc. And for each of those, we've got 3 features. So we've got 3 columns in our table. Each house is going to be its own row in the table. And those rows and columns, those features and samples together, those are what make up our X. Those are our things that we're going to be learning from. That is our input to our model. So we take those things, we measure our X, and we set that to one side. We write it down in our notebook. While that process is going on, for each house that we've looked at, we also want to work out what the price of that house is. Now, we only want to do that process for the subset of data that we are looking in detail at. So we do this as a one-off. just for this set of data. So an expert looks at the price of the house and assesses it, or maybe you look at the market records for recently sold houses and you do that slightly more intensive process, and we put that list of house prices in our Y column, so that each row now has the 3 features and a target and a Y. So now we've got all our data. We've done our initial data collection. We are now ready to start doing machine learning to it. The first thing to do before you just start throwing computers at something is to think about the kind of data you have, the shape of the data, the quality of the data, these kinds of things, and think about what relationships are there or do you want to discover between X and Y. In the example we had in the first chapter, a linear regression was just fine, but sometimes there's something more complicated. Deciding which model to use comes with experience and experimentation. It takes some time to discover what tools are out there and what possible things you could use to solve the problem you're trying to do. But let's say we've decided we want to use a linear regression, some kind of multivariate linear regression to represent these things. So we just choose our model, we import it into scikit-learn, let's say, and using our X and Y, we throw them at the machine learning. We let it do its thing. We call the .fit function, as we did before. The machine learning algorithm goes away and does its thing. We don't really have to care too much about how it works behind the scenes. We just trust that it's doing the right thing. At least at this point. Later on, you will want to understand more about how they work. But for now, we're happy just to learn it. Once it's finished learning about the data, we can now effectively throw our data away. You shouldn't. You should keep your data, but you no longer need it for that model to do anything useful. That model has internalized and simplified the relationships between that data down into a few internal parameters. And so now we can use that model to make predictions. It will look up the value of those internal parameters, stick them into some kind of equation, and give us back the answer. So that means that in a year's time, someone can come along to us and say, hi, I want to sell my house. We ask them how many rooms it's got, size of the garden, etc., etc., etc. We put those 3 numbers, which I'm going to designate X prime here for sake of argument because they're different to our X from before. We put those numbers into our model and it gives us back a estimate or prediction Y hat. Now Y hat is commonly used as the designator for a predicted value from a model. So you'll see that crop up quite a bit. Y hat is a prediction from a model. Now Y hat is just a prediction. We don't know that it's correct. There is, for any given house, an actual price that that house is worth. It might not be calculable, or it might be hard to calculate, but there's a real value out there. And so in principle, there is a measure of how right we are. If we imagine that person sold their house the next day, we would immediately know how right we were. Now, the measure of how right you are is sometimes easy to calculate and sometimes it's hard, but usually you can go a long way by simply subtracting your prediction from your real value. Now, you don't always know your real value, so that's not always easy. But if you do, just do a difference between the two of them, and that gives you back what's called the residual. Now, the residual is, in general, a measure of how good you did. It's what left over, is what residual means. So I've gone through this section here just to give you an idea of some of the terminology, give you a sense of how the flow of data works, and when things are used and when they stop being needed to be used. Now we've got a sense of the general process that you go through when you're trying to discover relationships in your data. I think it's worth taking a little step back and thinking about, before we throw machine learning at our models, what we can do to discover information about them, because the shape of our data, the type of our data, often strongly informs both what models we can use and how we should go about applying them. And I think one of the really important things to look at when you've got large data sets is looking at the correlation between your data. Now, correlation is one of these things which I feel is oversimplified when it's taught. And so I'm going to go through now what I feel is a better explanation of what correlation is and how it can be useful without going into the maths and so on. And then we're going to see situations where that nuanced opinion of it can actually start being quite useful. So when you're taught correlation at school or university, you're often told the full description, but it's often very, very quickly simplified down to how linearly related are these two parameters. By that I mean, as one parameter increases, how much does the other one increase, and vice versa. As one goes down, how much does the other one go down? That's a useful measure of data. It's a useful thing to understand. One of its real powers is the fact that it's really easy to calculate. Finding out linear relationships between data is almost trivial. There's a good number of easy to use and implement algorithms out there for finding out what the linear correlation between two values is. So I'm not trying to diminish the value of linear regression, but I think there is more to be said about regression than simply how linearly related things are. So you see on the screen here, there's a single plot. It's got an x and a y value. It's got a scatter in the middle. These two values here are strongly, positively, linearly correlated. As x increases, so does y, and as x decreases, so does y. So it's positive because they're both changing in the same direction. It's linear because there's no kind of strange shape to it. And they're correlated because, well, we've got a strong value for that correlation. But beyond linear correlation, I think there's more to be said. So I find it more useful to, instead of thinking about correlation in terms of as one goes up, how much does the other one go up, to instead think about in more detail how related the two sets of data are. Now, this is going to consume linear correlation, but it's a broader concept. So I like to think of it more in the sense of, if I know the value of one of the variables, how much do I know about the other? How much information do I have about y if I know the value of x? So looking at this parabola plot on the screen here, if I worked out what the linear correlation of this was, it would probably tell me that it's 0. If you plotted a line of best fit through it, a linear line, it would just be a straight horizontal line going straight through the middle. So that would be saying that the linear correlation of these two variables is 0, and so there's no relationship between the two of them, or at least that single parameter would simplify it down to that point and would say there's nothing that you can say. If you know x, you have no information about y. That's what linear correlation would tell us. Yet, clearly, looking at this plot, we know if we've got the value of x, we can make a really quite good guess about what y is. If x is 8, for example, well, y is about 15. There's no way that y is going to be 0 or 30. It's going to be about 15. Likewise, if x is 0, then y is going to be about 0. So there is definitely a strong correlation between these two things, but the linear correlation is 0. And this is why I think it's worth thinking more broadly than linear correlations. It comes into play as well because a lot of machine learning models are more than linear. They can discover superlinear relationships between things, and so us being able to describe them is a really useful thing to be able to do. In a more mathematical sense, the way that I like to think about correlation is really in terms of mutual information. And there's a really good, slightly mathsy Wikipedia page on mutual information, which describes this well, but it effectively comes down to how much information overlap or how much information sharing is there between x and y. If there's perfect information sharing, then they are completely overlapping in the Venn diagram, and so they're exactly the same piece of data. If there's no information sharing, then that's saying there's no correlation at all. But if there's some, then you can find out something about y from x, and probably vice versa. So thinking about mutual information and information overlap between your sets of data, I think is a better way of thinking about correlation than simply what is the single linear correlation value of these data. That said, we're going to jump straight into linear correlation because, as I said, it's really easy to calculate, so it's a good place to start. So I'm going to make a new notebook. I'm going to call this one correlation. And I'm going to load up some data. I'm going to import some pandas and numpy to get some data out. And I'm going to make a list of data, np.arange. This is going to make a range of numbers from 0 to 99. That's what the 100 means. I'm going to make a second variable, which is going to be exactly the same, except this one is multiplied by 2. If I plot this data by sticking it into a data frame, and have a look at the top of it, this is what we see. So we've got one column A, one column B. The numbers are both going up as the other one's going up. So immediately you're probably thinking, well, these are strongly positively correlated. That's a good place to start. So you're almost definitely correct. But with any data like this, there's some other things that we can learn about it along the way using the tools that Python provides. So this DataFrame DF, before we jump in and calculate the correlation, there's a function called describe, which is worth knowing about, which gives you very basic summary statistics about any given data frame. So when we run that, we see printed out how many values there are. There's 100 because we asked for 100 of them. The mean is about 50 of the first one. The second one, the mean is about 99. That's because the first one goes from 0 to 99, and the second one goes from 0 to 200-ish. Doing this describe thing is always a useful thing to do because it gives you a sense of the skew of your data, because you've got your percentiles, your standard deviations, things like that. So it's always worth having a look at your describe just to make sure you haven't got any weird values, weird outliers hanging out. It's a very nice, easy way to spot them. So a question there about why do we use a dictionary for this data frame here. I did that so that I could take this value here, which is this first column, and this value here in this second column, and give them column names so that it would be called A and B. If I did it just by passing a list, they wouldn't have had column names, and so we would lose track of which one was which. Once we've got our data frame, as well as calling describe on it, we can just go ahead and call the correlation function, or as they call it, core, because typing elation is far too much work apparently. And it gives us back a nice small table summarizing the correlation between the two values. First thing to point out on a correlation table like this, you might have come across these before, but if you haven't, then the diagonal terms here are telling us what is the correlation between A and A, and it's 1.0. And the second value here is telling us what's the correlation between B and B, also 1. We'd always expect the diagonal terms to be exactly 1 because each data set is always perfectly correlated with itself. It is the off-diagonal terms which are the more interesting ones. In this case, they are also still 1.0 because A is perfectly correlated with B, and inversely, B is perfectly correlated with A. Each side of this matrix here is often the exact copy of the other triangle, so the top right is always the same as the bottom left. So have a go at that yourself, run those commands, make sure it's working, then try tweaking your A and B up here so you get a pair of data which are inversely correlated with each other. So they've got negative correlation such that you end up with -1 on your off-diagonal terms. Okay, great. Abada posted in saying that you just multiplied that by -2. That's exactly the right idea. So, as I was saying, positive correlation is if one goes up, the other one goes up. Negative correlation is if one goes up, the other one goes down. So if we make that to be going down each time as A is increasing, B is decreasing, when we look at the correlation, we get -1 on the off diagonals. To get anything which isn't exactly -1 or 1, we'd have to add in some more interesting variants to our data, which require some random functions or just manually doing it. So instead of doing that by hand, let's have a look at some real data and see what we can learn about it. And also how we can do correlations between more than just one column and another column in a boring made-up data set. So again, we're going to have a look at scikit-learn's datasets area. This is where we got the diabetes dataset from before, but this time we are going to import the fetch California housing dataset, and we are going to save that as housing data equals that. So we're just grabbing the data there. I'm then going to put that housing data into a data frame so that it gets presented in a slightly nicer looking way. Data frame housing data dot data as the data in the table itself, and housing data columns as the column names are the feature names of that data set. I'm going to call that housing and I'm going to print out the first few rows of it so we can see what it looks like. So what we have here is a table of data. We have 1, 2, 3, 4, 5, 6, 7, 8 features. The target column is loaded separately, so these are all X. This is basically a big table of our X data. We've got 8 columns and we've got some number of rows. We'll have a look in a little bit and see how many rows there are probably. The meaning of these columns are each row is a census block in America. So it's 100, few hundred people or something like that. So it's some number of houses, but a small enough number that the variation within that little block should be quite small. And we're finding out for each of those blocks what the median income of the people who live there is, the average age of houses, average number of rooms, average number of bedrooms, the population of that area, so 300 people, 400 people, that kind of thing, average number of people per residence, and also where that census block is, so we have a bit of context for that stuff. So before, when we did the correlation function, we took our data frame and we plotted the core function for it, we called the core function for it, and that gave us back for each column the correlation with every other column. With only 2 columns, that's pretty boring, but the exact same syntax works no matter how many columns you have. So if we do housing.core here, it's going to think a little bit harder about it, but it should only take a fraction of a second. And it gives us back a table of data. This table has 8 columns and 8 rows. Again, the diagonal terms are all 1.0 because the age of a house is always correlated with the age of the same house. So we get 1 on all the diagonals, on this main diagonal, sorry. Again, notice that the 2 different halves of the matrix are exact copies of each other. So this value here, minus 0.11, is the same as this value here, minus 0.11. So you can often get away with just looking at one half of the table. Because we've now got this as a real Pandas data frame, we can drill down and find out more information about what's going on. So we can, let's actually call this core. And refer to that variable. So we can ask for the median income column. That's going to give us back that one column. Oh, I didn't run that cell. There we go. That gives us back that one column. And then from that column, we can extract out a row like average rooms. So this is going to tell us what is the correlation between the median income and the average rooms in this particular data set. And it gives us a slight positive correlation. So it's telling us that on average, as the income increases, so does the number of rooms, but it's not a solid increase. There's a fair bit of variance to it. So have a go running that code yourself, get that loaded in. And what I want you to do is to have a look at this table of data and see if you can pick out by eye what the most negative and the most positive correlations are in that table. See if you can do it by eye. If you want to, you can have a go at writing some code to do it. It's perfectly possible. But doing it by eye is the first step in that process to get a sense of how this stuff works. So I'll just give you a minute or so to look at that by eye. If you want to have a go at the code, feel free to do it now or later on. And then we'll have a little discussion about what we're seeing here. Could anyone tell me what they think is the strongest negative correlation? Okay, great. And what is the strongest positive correlation? Yeah, rooms to bedrooms is a strong correlation between there in the positive direction. Now that positive correlation makes a lot of sense. We'd expect that if houses have got more bedrooms, they therefore got more rooms and vice versa. However, that process probably wasn't painless. Scanning through a table by eye, going up and down these columns one by one is hard work. You have to peer into it and try and look at the numbers, remember what the biggest or smallest number you've seen is, and so on. And so, as you all know, plotting large amounts of data as a table isn't the right way to do it. We want to visualize it in some way and make it easy for our eyes to see. So we are going to plot this same set of data here, but in a visual way. So let's have a look at how we do that. I'm going to use a package called Seaborn, which is a plotting package which builds on Matplotlib but adds in a bit more functionality, slightly nicer API at times, but it adds in at least one default, easy to draw matrix plotting of correlation functions, which is going to be useful for what we want here. We're going to import it as SNS because that's convention. And we're going to do SNS dot heat map, and we just pass in that table. In order to make this look a bit nicer, we're also going to give it a color map so that 0 is a nice neutral white, strong numbers are going to be blue, and strong negative numbers are going to be red. So to make a diverging color map, we are also going to do SNS dot diverging palette. And this is one of the things that Seaborn provides, is nice, easy to use functions like diverging palette, where you specify where you want to start, where you want to end up, and that you want it to be used as a color map. And we pass that to our plotting function with cmap equals cmap. And when we plot this, we get our, actually I'm going to do 220 because it's a slightly nicer blue. There we go. So here, much more easily, we can immediately spot our positive and our negative strong correlations. So looking at the upper end of this graph, we see that blue is used for a correlation of 1. We see strong blues along the diagonal. We also see a next strongest blue between average bedrooms and average rooms. So we're immediately seeing there's a strong correlation there. We didn't have to scour the numbers, we just plot it and we get it out straight away. And so I would recommend the first thing you do with your data is grab it in, look at some of the summary statistics, have a look at the correlation between them. It's worth looking at the table, but don't spend too much time on it. It's a good idea to go as quickly to a plot as you can, because you're going to be able to spot interesting things much more quickly. This here is showing the linear correlation between the variables. So it's telling us that the linear relationship between average bedrooms and average rooms is, 0.32 we saw before, so it's relatively strong. But it isn't necessarily telling us the whole story. We saw before that linear correlation is only a part of how you can describe the relationship between data. It doesn't give us enough information to learn everything about it. So we want to be able to look at the relationship between these variables in a more nuanced way than reducing it down to a single number representing the linear correlation between the two variables. Linear correlation gives us a nice square rectangle on this plot, but we want to get some more information, more detailed information about what's going on. And so Pandas provides a function to help us do this, and it is called scatter matrix. So Pandas, which is how we've been loading our data, has got a plotting sub package, and from there we can import scatter matrix. You use scatter matrix. I'm going to assign it to a variable here because otherwise it's going to print a load of nonsense to the screen, with scatter underscore matrix, and we pass it housing. By default it's going to plot it quite small, and so I am going to pass in the fig size argument, which accepts for some reason in inches the size of the plot, and so let's make it 16 inches square because I know that's about right. This will take a minute to plot, so do be patient with it. It's plotting all of the data, but it will eventually get there. So have a go at doing that yourself, get that plot up, and then I'm going to talk through how you read this plot because it's not always immediately obvious. There we go. So that's showing up on my screen now. So while yours is running, I'm actually going to switch to the notes and get the picture because it's easier to make it big. That is the plot of all of the data. It's effectively the same information as we had before with the correlation matrix, but instead of the relationship between each variable and each other being summarized down to a single variable, it's instead plotting the scatter plot of the relationship between the two. So the best place to look first is at the average bedrooms and average rooms column and row. So that's row 4 and column 3, for example. They had a strong positive correlation, and looking at the data here, we can see why. There was definitely a longitudinal blob going from the bottom left towards the top right. That is therefore making sense. As one goes up, the other one goes up. The linear correlation is strong, and so we're seeing something going on there. But looking at the other parameters on this plot, some of them are definitely a bit more nuanced than just a longitudinal blob. For starters, many of them are very, very skewed distribution. In fact, almost all of them are very skewed distributions. The easiest way to see the skew on the distribution is to look at the diagonals. Looking at the very top left square, for example, there we see what would be the scatter plot between median income and median income. They realised that actually there's no point in drawing that scatter plot, and so they repurposed the diagonal terms on this plot to be a histogram of that variable. So this here is just a distribution of how many entries there are with a median income that's at the low end, at the medium end, and then up towards the high end at 15. So you see here there's a skewed distribution slightly towards the bottom end, but it's not completely skewed across. House age is also nicely balanced. House ages go up to about 60 years or so that's traditional American houses not being very old. And you see many of them are much, much younger than that. When we got into the average rooms and average bedrooms graphs, however, we see there's a very, very skewed distribution. So much so that it looks like it's entirely inside the first bin and nothing in any of the others. Now, it can't be there's nothing in the others, otherwise those bins wouldn't exist. It's simply that this first bin, if you look at the x-axis, is covering everything from about 1 room up to 10 rooms or something. And I think it's fair to say that most houses have 10 or fewer rooms. These larger entries up here, of which there are many fewer, will be mansions or tower blocks or mistakes in the data, potentially. So those are very, very skewed distributions. Down in the bottom left, we see there's sort of the distribution between median income and latitude. There's some structure here. It's not linearly correlated in any sense, but there's definitely some information there. So there's something that we can do with that, potentially. There's something that a machine learning model could discover about that relationship. The last thing to point out on this plot is I was asking before if you could point out what the strongest negative correlation on that table was, and you all pointed out that it was the correlation between latitude and longitude. And that doesn't necessarily make sense to me. Why would the latitude and longitude be correlated on a table like that, on a piece of data like this? We don't expect, if you think about a map of the UK, that as the latitude goes up, the longitude should go up, because most places are kind of square blobs. Most geographical entities are roundish. But yet here we were seeing a very, very strong negative correlation. And more interestingly, that is consistent with what we're seeing in our scatter plots here. We see a very strong negative slew of data going from the top left to the bottom right when we're looking at our scatter plots down there in the bottom right. Now, has anyone got any ideas why we might be seeing this kind of correlation between latitude and longitude on this data set when we wouldn't normally expect there to be any relationship between them at all? Has anyone got any ideas? So Joe's saying it could be the coast. Yeah, so absolutely. There's some geographical things going on here. Clearly, where the coast is going to come into effect. It's going to bound the data in some way. So that's going to affect stuff. But the UK has a coast, and I don't think the UK would have this kind of correlation. Anyone else got any other ideas? Yep, okay, so Abada's hit the nail on the head. Think about it for a moment. What do you get if you plot the longitude against the latitude of something? What you get is a map. If you plot the longitude and latitude of all of the census points on a grid, you get a map of all of those census points. It so happens that California is a shape which goes from the top left to the bottom right. It's an artifact of the location as to where this data was collected. This same data set in another state in the US, even with very similar conditions, because it would be a different shape, would have completely different correlation between its latitude and longitude. It is a particular feature of this data that we're seeing this. It's not necessarily something that we would expect. So we've accidentally drawn a map here without realizing what we were doing. I believe that it's the one on the top right that's the map and the bottom left is something else. In fact, if you look at it, you can almost see San Francisco going around the bay, though it's a little bit blurry due to some desert and mountains that get in the way a little bit. Yeah, exactly, Jafe. It suggests people on this one live in a line between those two things, but because we've taken a subset of our data by choosing California, it's kind of imposed that condition on the data when it wouldn't necessarily be there in the first place. It's not a natural thing, it is a data artifact. And this is something that's worth being really, really careful about when you're collecting and analysing data. We could have looked at our data here, thought that this was just a spurious bit of correlation, ignored it, carried on, trained a model based on this stuff to predict what the price of a given house would be, based on its longitude, its latitude, its occupation, the number of bedrooms, etc. We get a model which predicts it really well for California. We do our testing and our validation, and it would all be working well. Even if we took that model to somewhere else in the US, which is similar-ish, somewhere like, I don't know, New York or Washington, you would apply it and suddenly the whole model would collapse and fall apart because the longitude and latitude data has been baked into the model when really it's not relevant to it at all. It's found a relationship there, but it's not a general relationship. It's only a relationship which is specific to the place where the data was collected. It's a Californian relationship. It's not general. So that's a really obvious example once you see it, but the thing to remember is that all of your data is biased in this same way. You always have to be careful about what implicit or explicit assumptions have gone into the data collection, the data sampling, and what models you've chosen. This one here, you can spot it quite quickly. It jumps out when you look at the correlation. You see that there's some structure to it when you look at the data scattered on a plot like this. But you're not seeing it in the other parameters where there is also likely some data relationships which are slightly more hidden. So it's always worth being careful, thinking about where your data is coming from, how you're choosing to analyze it before you put it into your models, and where you then use that model, both elsewhere in the world and over time. Of course, a house price model isn't going to work if it was trained in the 80s and is being used in the 2020s. It's going to give you the wrong answer. All models have bounds, and part of your job as a data scientist is to think really carefully about what those bounds are, both to make them as broad as possible and to understand them so that you don't use a model in a place that it shouldn't be used. So the last thing I wanted to mention about correlation now is why we care about correlation in the context of machine learning. So there are two kind of competing ideas when it comes, or two competing concepts when it comes to correlations. The first is that between the features that go into your X, the things that you're training your model based on, for example here, average rooms and population, we don't want there to be a strong correlation between those two parameters. And this comes back to thinking about it in terms of information sharing. If we looked at average bedrooms and average rooms, they are strongly positively correlated. So we could train our model ignoring one of the two of them. So we just do it with average bedrooms and we'd get perhaps a good model coming out. If we then add in the average rooms parameter, we're not going to be adding much more information into our model because the information overlap between something that's already there is quite large. So we're adding in more data, we're adding in more processing time, but we're not adding in more information. And so that's going to make our model train slower, potentially behave worse, for very little benefit. So looking at the correlation between your variables and thinking about what variables you no longer need, that you can get rid of, or that aren't going to give you any useful information because maybe their skew is so much that they are all inside one bin and you're never going to be able to see anything, is a worthwhile exercise. There are techniques you can do to re-parameterize your features. There's things called dimensionality reduction algorithms. For example, principal component analysis can work out a new set of dimensions which don't have correlations between them, which are orthogonal to each other. And that's a kind of technique which you might want to apply to your data, and there's some information at the end of the course about where you can learn more about that. The other thing to think about with correlation is that while you don't want correlation between your various input values, you do want some kind of correlation or mutual information between a feature and your target. In fact, you need information overlap of some degree between what you're putting in and where you're trying to get to. Otherwise, there's no predictive power. If we were putting into this plot here the favourite colour of the people in each of those areas, that would have no correlation whatsoever with the price of the house. And so that would be a useless piece of information to put in. So looking at the correlation between your inputs and your output is worthwhile as well, because if they've got a strong correlation, then you're going to be able to get a lot of information out of it. And by strong correlation, I mean more than just a strong linear correlation. I mean a strong correlation in the broader sense of what kind of structure is there to the data. So between your features, you don't want correlation, but between your feature and your target, you often do want correlation. The next technique I wanted to cover was clustering. So if you remember near the beginning of the session, I was talking about the different kinds of machine learning. I was saying there was the supervised techniques, which have an X and a Y, and you're trying to find the relationship between X and Y. And there was the other techniques, which were the unsupervised techniques. And these are tools where you show the algorithm your data, and it just tries to learn some kind of information from the data or extract some kind of internal data from it. Now, clustering is probably the most famous example of unsupervised learning. And when I was first learning about unsupervised learning, when it first came across the concept, I was very confused by the whole thing because I couldn't understand how you can have a computer algorithm which learns about your data without knowing where it's supposed to end up. So hopefully I'm going to be able to show you how that is possible and how it works and the kinds of questions that you can answer about it. So we're not going to worry too much about the exact technical definition of how k-means clustering works. We're going to dive in and start just doing stuff with it, but I will then probably refer back to this and explain to you about how the way that this algorithm is implemented imposes certain limitations on what's possible to do with it. So I've made myself a new notebook here, and so I'm going to start off by making some data. Again, I'm going to start from scikit-learn. And scikit-learn's datasets module, as well as having built-in datasets like that California dataset or the diabetes dataset, also has some functions which allow us to generate data, sort of generate toy data. So in there is a function called make blobs. Can I just check that people can hear me okay? Someone in the chat was saying they couldn't. I'm assuming Lester can since he's narrating. Yeah, Lester can hear me at least, so okay, great. Welcome back, 7. So we've got our make blobs function. We can call that function, and it is unsurprisingly going to make us some blobs. There's some parameters we can pass in, of course. For example, how many sub-blobs do we want? How many data sample points do we want? And we want to do a largish number like 500. Then we tell it how many blobs we want. It calls them how many blob centers do we want, and we tell it that we want, let's say, 4. And because it's going to be generating these blobs randomly, and I want to first of all make sure that you're seeing the same random as I am, I'm also going to set the random seed. Now the random seed will make sure that while it's, the random state, sorry, will make sure that while it's technically kind of doing something pseudo-random, it's all going to be starting from the same place, and so we're all going to end up with the same set of pseudo-random numbers. And through extensive research before when I was writing the session, I found out that 6 is a good number. So let's go ahead and just use 6 for now. This returns 2 variables. It returns the data, i.e. the actual samples that make up the blobs, as well as which cluster each of those blobs originated from. So true labels. You can think of this as your X and your Y. I was saying before that since this is an unsupervised technique, we're not going to be using Y, and indeed we're not. We're going to not use this true labels variable at all in the training of our model. We're only going to use it to check how well we're doing, basically, if at all. So it's there as a cross-check for our educational purposes. It's not being used by the machine learning algorithm. So you run that and it generates the data. We then want to have a look at what this data looks like, because I'm sure you're all having trouble visualizing exactly what I'm talking about here. So let's go ahead and do a plot. I'm going to put the data into a Pandas DataFrame first, because I like the Pandas plotting interface. If you're comfortable with plain old matplotlib, then feel free to use that, but I like the Pandas model. The points are then going to be that same data we got back from the make blobs function, but passed into a data frame. And I'm going to label the 2 columns as x1 and x2. Not x and y, because that would confuse with the features and targets that we had before. These are both effectively features of our data. We're not worrying about y here, because it's an unsupervised model, and so there's no y data. If the y data is anywhere, it's in this variable here, and it's going to stay there, out of the way, without us cheating by looking at it. Let's then plot our data, points.plot.scatter, and plot the x1 column against the x2 column. And there we have it. We have 4 different blobs, and we have 500 total samples, 500 little circles making up our plot. So first of all, I'm just going to ask you to just run those 2 lines of code. Make sure you've got that working, and you should see exactly the same blobs as I do. The same outliers, the same places of the centers, all that being identical. If you don't see something that's identical, make sure you set your random state correctly, and your number of samples and your number of centers. If you still get something different, well, it might be because you're on a different version, but I think they're relatively consistent. So have a go at doing that, give you 30 seconds, and then we'll move on to applying some machine learning to it. So we have here our x1 and our x2. These are input features to our model, in the same way that the size of the garden and the number of bedrooms are input features of the model. You might find that if you plotted size of garden against number of bedrooms, you wouldn't just see a spattering of data, you might see localized clusters of data in your output. Clustering is often used with large census data. For example, when you're doing a census for each individual or for each household, you'll end up with hundreds of different features describing that household. As a way of reducing the amount of information you need to keep about them, you might take a few of those features and simplify them down into some categories. For example, this is often done to put people into socioeconomic categories, whether they're working class, middle class, upper class, or whatever the new titles for these things are. Based on various features about the household to do with income and education and where in the country they live and so on, you might be able to cluster those features, find subsets of people which largely fall into one of a number of categories, and at that point you can effectively throw away those multiple features and replace them with one categorical feature, which is just which cluster are they part of, which can simplify analysis and also simplify human understanding of what's going on, because it allows you to take a whole bunch of features and put them into buckets and give them names, and that's useful for humans to understand what's happening. In order to analyze our data, let's go ahead and call the clustering algorithm. So again, from scikit-learn.cluster this time, not from linear model, but from cluster, we are going to import k-means. So k-means is a particular kind of clustering algorithm. It's called k-means because when you're deciding how you want to cluster your model, you decide in advance how many centers you want it to cluster it into. Another term for a cluster center is the cluster mean. And so if you want k means, you're saying you want k clusters, where k is a number between 0 and whatever. In our case here, we want to find 4 clusters, and so k is going to be 4. So we want to find 4 means. Same as before, we call our model like a function because it's a class we want to construct. There is a hyperparameter, which is the number of clusters. Deciding on how many clusters you want to use for your model is an art in itself. For example, when they were looking to try and work out how many different socioeconomic classes there are, and thinking in the last census we had, they changed the number and they reclassified them, they would effectively have tried a bunch of different number of clusters, seen which of those divisions worked best and gave them the best explainability, and then stuck with that. There's no absolute truth, except in the cases where it's been generated from something which has absolute truth, and we'll see an example of that a little bit later. In this case here, we generated this with 4 clusters, and so when we plot it, we also see there are 4 clusters, so of course k will be 4. We are then immediately going to call the fit function on it and pass in our points table. That is this table here, which is a data frame with 2 columns, x1 and x2, and 500 samples. I'm going to assign that to a variable. When I call this, it goes away, it does the algorithm, it's done the machine learning on those 500 points, and it's now put them all into categories. Have a go at running yourself that now, make sure you get that successfully running, and then we'll look about how we can extract the data from the model. Alistair's asking, can you get an algorithm to decide how many clusters there are? There are some techniques. I've never been very convinced by any of them. There's one where you look at effectively how good the fit is divided by the number of clusters, and you look at that for a different number of clusters, and you find the point at which that curve kinks most sharply. It's called, I think, the elbow finding technique, because when you plot the graph, it has a sort of an elbow shape, and you look for the point down in the bottom left where you've got fewer clusters but also fewer levels of uncertainty. If you actually try doing this, you'll find that there's never a single clear point at which you can say there are this many clusters. And so really, I would primarily say let the number of clusters be informed by both your data and by the underlying model which you think that you're representing, and also by what data you're looking to extract. It often comes from starting at the point of, I want to divide my data into this many blobs, or I've looked at my data and I've seen it's probably this many. Beyond that, you can fiddle and you might find that, oh, there's 10 or 11 or 12. And as you're changing those number of clusters, it could massively vary whether a certain sample goes into one cluster or another. And so you need to think about, what does that mean for your data? There's no magical way of doing it. There are tools that can help, but there's no magical solution. Once you've got your algorithm run, you've got your k-means object, which is containing the result of the fit. Let's go and see what we can see about what's inside it. So, k-means is the name of our object. Dot cluster underscore centers, spelt the American way, with an underscore at the end. Again, the underscore at the end is telling us that this is a computed parameter by the model. If we look at what that gives us back, it gives us back a numpy array. I like to convert all of my numpy arrays into Pandas DataFrames because it prints them out more nicely. So let's make a data frame out of that and call the columns, because I know what the columns are called because they're the same columns we started with, are x1 and x2. Cluster centers, I'll use their spelling as well, and let's have a look at it. Oh, I've missed a bracket off the end. There we go, same data. If I array these so we can see them both on the screen at the same time, we look at cluster 0, it's saying that its x1 is at 6.5-ish, x1 is at 6.5. That's looking like it's lining up with one of the right-hand two clusters. Its x2 value is at -9, which if you look at the x2 axis is showing that that is pointing at the center of the bottommost cluster. If you looked at the corresponding x1, x2 coordinates for the other cluster centers, you'd see they would lie in the center of those three other blobs. Of course, doing that by hand, by looking at it visually, is no fun, so let's use the computer to do our job for us. We want to do the same thing we did before, points.plot.scatter x1 against x2. We're going to assign that to a variable, and then we are going to cluster centers.plot.scatter x1 against x2. So we're plotting the data points against each other, and we're plotting the data centers against each other. I'm going to tell it that we want to plot on the same axis. I'm going to say I want the color to be red for the cluster centers. I want the size to be a little bit bigger. These are all parameters I've worked out earlier because I prepared. And I'm going to use a marker of an X. So now when I plot this, we get our original clusters and we get a big red X printed on top of each of those clusters as to where the k-means algorithm thinks the cluster center has ended up. So have a go at that yourself, run those lines of code, get the cluster centers extracted and then plot it on a graph and make sure it's showing up something like this. I'll give you a minute for that and then I'll move on. Alistair's asking, how would clustering work on log scales? It would work fine. So if you take your data and you log your data, you can then cluster it fine. The thing to remember with k-means clustering specifically is that it works on a circular basis. The way it assigns points to clusters and then cluster centers to the center of the points that are on that cluster is with a traditional Euclidean distance, the Pythagorean distance of x squared or x1 squared plus x2 squared square rooted. And so it's implicitly working in a circle around the cluster center to find the points which are nearest to it. If your data has been logged and so it's skewed it in various ways, it may no longer be circularish data. And so your clustering algorithm is going to struggle to solve it. I've got some examples in a little bit of types of data where k-means fails and other clustering algorithms succeed. So we'll have a look at those in a little while and see the pros and cons of various algorithms and how you can go about solving it. And log scales come into play in that same kind of idea to do with transformations of your data. Yes, so I would try and make it so that the actual numerical parameters that are associated with each feature appear linear. So if my data was distributed exponentially, I would log my data so that the new parameter is effectively a linear scale of the exponent, so that my data now appears linear, even though the original data parameter was exponential. So by logging it, I've linearized it a bit more, made it more circular, made it more regular, so that clustering is going to work better on it. So we plotted the graph here by finding the, where has it gone? The k-means.clusterCenters underscore parameter, which has given us 4 pieces of information because we set k to be 4. There is one other piece of information that the k-means clustering algorithm has provided for us, and that is k-means.labels. So you remember right at the beginning, if I scroll up, we extracted out our true labels. That was a number 0, 1, 2 or 3 for each of the sample points as to which cluster they were generated from. What the k-means algorithm has done is that when looking at this data without knowing what true labels is, it has, during its process, assigned each sample to a particular cluster, and it's remembered which cluster it's in. Obviously, throughout the algorithm doing its work, the label associated with each sample point is going to change as it's iterating towards a solution. But by the time it's finished, each sample will have a particular label. So we have a look at k-means.labels. We see it's a big old array, where it's saying that the first sample is in cluster 3, whatever that means. Second sample is in cluster 0, whatever that means, etc., etc. Now these are effectively random cluster numbers. There's no reason to assume that the clusters are ordered from top left to bottom right. In fact, we saw before that cluster 0 was the bottommost cluster. But these numbers here do relate to our cluster numbers in our table here. So we can relate these two things together. But what we can do with that is we can use this to plot something. So let's again plot our points as a scatter plot, x1 against x2. We then are going to set the colour of each sample, of each small dot, to be based on its label that the k-means cluster has worked out it thinks it's part of. And so we do that by setting the colour to be equal to k-means.labels. That works because matplotlib by default has a colour map which has a colour associated with each integer value. And so it's going to colour each of these based after whatever colour it thinks is colour 0, colour 1, colour 2 and colour 3. In fact, we can tell it which set of colours we want it to use by using color map, and let's use dark 2, and let's not print a colour bar because we don't need to see one, because we know what our different colours mean. And so now when we plot this, this is telling us which cluster the algorithm decided each point belongs to. And you can see that on the whole it seems like it's done a decent job. But there are clearly some points in here where there is potentially some ambiguity. First, my eye is drawn towards that yellow point, which is halfway between the grey and the yellowy-orange clusters in the middle there. To me, it looks like it's halfway in between. It's not going to be obvious which cluster it's falling into. It could be one, it could be the other. If we let the algorithm run for longer or for slightly less time, it might have ended up in a different cluster. Similarly for the green and orange points between the green and orange clusters, those 2 points are very close together, so you can easily believe that both of them could have ended up in one or both in the other, depending on how the iteration progressed. And as Alistair asks in the chat, how can you get k-means to infer probability distributions of which cluster each point belongs to? Not by default as it comes out. One technique you could do is, as the thing is iterating through, or once it's finished iterating, iterate it for a longer time, see if over that time period any points change from one cluster to another. And that's representing the clustering algorithm being unsure as to which cluster it belongs to. You could then look at how much time it spends in one cluster or another and assign to that some kind of frequentist probability as to which cluster it belongs to. But I don't know for sure whether that is necessarily statistically rigorous, but it would certainly give you a featureful idea of which points are the contentious ones. So what I'm going to ask you to do now is, as you've already been doing, follow through and do these copy the code examples that I've been doing. But if we have a look on the course notes, the first set of exercises on here, just after that clustering section, first of all have a go at running that through again, but try changing the random state of the original blob generation. You have to rerun the random state and then rerun all of the cells afterwards. See how that affects both the original distribution. See what happens in the situations where you end up with blobs overlapping, how well the clustering algorithm is able to distinguish the two of them. Make sure you understand about what's going on there, and if you have any questions, do please ask in the chat. Once you've had a little play with that, move on to exercise 2, where we're going to load in this iris dataset, which is from the scikit-learn datasets library. There's an iris function. You can load the data there into a data frame by copying this code here. So once you've got this iris thing, and then have a go at doing the clustering on this iris dataset. I do note this iris dataset has 4 features. I cheated a bit here with our x1 and x2 because it's easy to plot x1 against x2 on a 2D plot. Since the iris dataset has got 4 features, you'll have to think a bit hard about how you plot it. And as a trick, I'll remind you that you can use the scatter plot stuff we did for the correlation section on the page before, scatter matrix I think it was called. And if you get to it or you want to have a go, there's also an optional third exercise at which you can start looking at the inertia of these objects. I'll go through the answer to the exercise afterwards to explain what's going on, and exercise 3 comes on a little bit to the question about knowing how many clusters you should use and the techniques which I don't think are always that useful. Have a go with those, spend a few minutes on them, and let me know in the chat if you have any questions. So Serban's got a question there and says, when 2 blobs are very close, it separates them linearly. So let's have a look at what's going on there. So let's do random state. There we go. So when we look at the centers that come out of this. Oh, I need to rerun the algorithm. We see that it's put the 2 centers in the middle of what are probably the 2 blobs at the top of that section there. If we look at how it's assigned the labels, however, we'll see that the line between them is very much a straight line. And so what's going on inside k-means is that it keeps track of where the centers are as it iterates through. They start randomly. It then looks for it looks at each sample and works out which cluster center is nearest to it. Based on all of the samples which are therefore nearest to a given cluster, they will become part of that cluster. It moves the cluster center to the average of all the points in there and then iterates that process again. But because at the core of that, it's looking to see which cluster is nearest to a given data point, you end up with very, very straight lines of separation between cluster centers. This is very similar to a thing called Voronoi tessellation, which is a really interesting way of dividing up a plane based on random centers. You get a very similar thing happening here with k-means. And so even though our metric is circular, in that it's circularly isometric, you end up getting straight lines separating your clusters because along that line, it is equidistant from one center and the other. And that's why you get a nice sharp straight line between the purple and the brown clusters down here, for example. That's maybe a better example. These 2 clusters are very close together. It's not obvious to me at all how it should be able to distinguish those into 2 clusters. It's probably just put 2 there because there are more data points in that top left cluster. And that means when we plot it, we again see there's a very straight line of separation between the grey cluster and the purpley cluster. Again, this is due to the metric that's being used. It's which cluster center am I nearest to? So you end up with a straight line separating the 2 of them. Let's have a look at the iris dataset next then. So this was exercise 2. So let's start by going from scikit-learn.datasets import load iris. And then I'm going to copy the line that I gave you, which is loading that into a data frame. And let's have a look. So here we have a table. It has 150 samples and it has 4 features. Based on those 4 features, we want to be able to work out what the species of this is. So we know in advance, and in fact we can find out by running asking it for the number of target names, number of categories, number of classes at the end, and have a look at what that is. And there are 3, so there's 3 different species here. And we want to use these 4 features to group each sample into one of 3 clusters. Once we know where the cluster centers are, we can then bring along new fresh data from the wild and work out which cluster center it's nearest to, and therefore make an estimate as to which iris species this flower we've just found in our garden is, for example. So we are going to call our k-means function again, and we are going to pass in n clusters equals number of iris species. So this is a situation where we've worked out in advance how many clusters we should have because we know how many species we've measured our data from. And as long as any new data we put in belongs to one of those 3 species, this is going to work well. Then we fit it by passing in the iris table of data. I'm going to assign that to, again, I'm going to call it k-means because I'm unimaginative. That's now done the algorithm. It's worked out how these things are related to each other. That means we can now plot the scatter matrix. Because we've got multidimensional data, it's good to have something which can represent that multidimensional data. I'm going to plot our iris. I'm going to set the fig size to be, again, 16 by 16 to make it nice and large. And I'm going to set the color based on the calculated labels from the algorithm. And here we have our iris data. So we have, again, I'm going to switch to the notes to see this picture because it's going to be easier to make large. We have our 4 features. Here we have the sepal length and the sepal width. Sepals are part of the flower in some way. I'm not a botanist, don't really ask me. And we've got the petal length and the petal width. I know what petals are, but I don't know how they're different from sepals. So we've got the length and the width of 2 different parts of the flower. And we have taken measurements of 150 flowers, and we have tried to work out, based on how those different variables relate to each other in 4-dimensional space, where the clusters sit. And so that's what the k-means clustering algorithm has attempted to do here. Now, I apologise for the colours. It's hard with this plot to get the colours to look up well. So if you can't see over the network, do have a look in the course notes on your own computer, and the colours might show up a bit better there. But the first thing to point out is that we've got 3 different colours. We've got a purpley colour, sort of a greenish colour, and a yellowish colour. And the other thing is that each of these panels is a projection of 2 of those dimensions against each other. So it's 4-dimensional data, but each of these scatter plots is a 2-dimensional projection of that data. So we end up with 6 different 2-dimensional projections of that 4-dimensional data. It's a little bit hard to think about multidimensional data. This is pretty much the best we can do. Looking at the purplish sample, we see that in almost all of the projections, that is well separated from the other cluster. So it's not surprising that k-means is able to easily pull apart that and draw a nice clear line separating it from the others. Now remember, when we were in 2 dimensions, we had a 2-dimensional, a 2-parameter line separating them. You can parameterize it with 2 variables, gradient and y-intercept effectively. Because we're here in 4 dimensions, we effectively have a 4-dimensional line separating each of our clusters hard to visualize, but imagine in 3 dimensions you would have spheres around each cluster. So in 4 dimensions we've got kind of 4-dimensional spheres or Voronoi cells. So the purple one is well separated, but as you can see in a lot of these, for example, the first row, second column, you see that there the yellow and the blue points are actually overlapping with each other, which might seem strange given that with our clustering we were seeing a nice strict line separating our 2 clusters. But the reason we're able to get information as to which cluster the green and the yellow belong to is because the clustering algorithm isn't working on each 2D projection individually, it's working on all of the 4-dimensional data all at once. And so it's managed to find a 4-dimensional line separating the yellow and the green, such that when you project it down, that projection line is kind of going up and down, but also slightly into the screen. And so it's separating the yellow and the green kind of above each other, if you think about if there were a 3rd dimension. And so even though in each of those projections there's not necessarily a clear separation, once you take into account all of the 6 projections, it starts being a much, much better way of separating your data. Also note that on the whole, thinking back to our correlation chapter, there isn't, in our correlation chapter we were saying that we wanted there to not be correlation between each of our features. We didn't want, for example, if we were doing a supervised model here, petal width and petal length to be correlated with each other. Now in clustering datasets, it's a different story. Because in a clustering dataset, you care less about the linear or scaling variation between the 2 of them. We don't care if petal width and petal length go up with each other necessarily. What we care about is how distinct they are clustered on the screen, not simply their covariance between the 2 of them. So it's a slightly more nuanced thing you need to think about with clustering compared to correlation with supervised learning, which again is why plotting on a graph like this is a really, really useful way of visualizing what your data is doing. So here we have our make blobs again. We've got our same centers before. We've got 500 samples, 4 centers, random state of 6. So it's going to be exactly the same data. As we loop through, trying out different numbers of clusters. So we're going to call k-means with n clusters equals 2, then 3, then 4, then 5, then 6, then 7. And for each of those times round, we are going to ask of the model how well it's feeling by the end. And the way you do that in scikit-learn is ask for the .inertia parameter. Now the inertia parameter basically relates to, by the time the algorithm has finished its job, how much were the points still jumping around? How much were the cluster centers still varying? i.e. how much inertia did they still have by the time it called it quits and said, I've finished clustering. So low inertias are good because that means that by the time the algorithm's finished, all the cluster centers had settled. A high inertia means that while the algorithm was running, those centers were jumping around a lot, and so it still hadn't found a good solution. So we want low inertias. We then take the inertia values for each of those numbers of clusters, and we plot a graph of one against the other. And this is getting to that elbow plot thing I was alluding to earlier. Number of clusters on the x-axis, so 2, 3, 4, 5, 6, 7 clusters. The inertia is, I don't know what units it's in, but lower numbers are a better fit. And so you see by the time you've got to 7 clusters, it's managed to settle down quite well and work out where everything should be. However, we know there's 4 clusters, so we look at the value for 4 and we see, well, 4 got quite low as well. So the idea with these plots is you're supposed to be able to look sort of bottom left, see where it elbows and choose that as your number of clusters. But I've never ever been able to look at one of these plots and spot an obvious elbow. I wouldn't be able to pick between 3 and 4 on this unless I spent a lot more time doing this. So it's not always, to me, the most useful technique to decide how many clusters you should use. A more useful technique is to think about your data and think about the question you're asking, and see if that's going to give you useful information at the end of the day. That said, plotting an inertia curve over a couple of numbers of clusters is often a nice thing to do in case you spot any particularly interesting features. As I was alluding to before, and Al was asking when he was saying about logging your data and so on, there are limits to what k-means clustering can do. We saw, for example, that when you've got 2 blobs that are very close together, it's going to struggle to identify which cluster the points belong to. That somewhat is a fundamental restriction on what you can possibly expect a computer to guess from your data, but you can somewhat use some models if you know how the data is being generated to work out how you should cluster your data. So there are more advanced techniques you could apply. So k-means, which the clustering algorithm we're using here, is good because it's simple, fast, and easy to implement, but it famously has problems with clusters which are elongated. And so I'm going to switch now to a picture which is in the notes, so feel free to look at it there, which I've stolen from the scikit-learn documentation. So what we have here is a column for each different clustering algorithm. These are all fundamentally doing the same thing, just with different implementations. And each row here is a particular example of potentially tricky data, although I guess that row 5 is supposedly easy data. The k-means algorithm we've been using is that very first column there. So if you look at row 5, you see it's done the job just fine, like we saw. But looking at row 4, where we've got these elongated blobs, this is somewhere where k-means famously struggles. And that's because, as I was saying before, it always makes the assumption that the data you're working on is circularly distributed, or hyperspherically distributed if you're working in more dimensions. And that's because it always works by putting the center of the cluster in a place and working out the linear distance from there to any of the points. And that means if you've got two clusters which are next to each other and elongated, if you put the cluster in the center of one of them, then the points in the center of the other cluster are going to be nearer to that center than the points at the end of the elongated cluster that you've selected. And so it's going to do a bad job of working out which points each cluster should have in them. Looking across the row, we see there are other algorithms which do a better job because they do various other bits of transformation to your data. But there is other stuff we can do to our data first before we use k-means to kind of make it work a bit better. So one of them is dimensionality reduction. I mentioned principal component analysis earlier. One of the things that principal component analysis can do is take something that looks like the stuff on row 4 and turn it into the stuff that looks like row 5. And it does that by working out the principal components of the data set, which would be along the length of the blob and across the width of the blob, and renormalizing the data so that it becomes more circular. Then you can apply k-means to your data set and you get it working. So by combining a dimensionality reduction like PCA with k-means, you can deal with a lot of messy data. That, however, isn't going to help with the stuff on the first row. The first row, PCA isn't going to give you anything directly useful because PCA tends to work with linear models. So here you can see that k-means has failed because while the outer and the inner ring are distinct, they share a center. They've got the same cluster center, and so it's not going to be able to distinguish which point each cluster should be in. So what you would normally do with this kind of data is look at it by hand and think about how you could transform the data mathematically to make it more easily clusterable. So one thing you could do with that first row, for example, is instead of plotting it in x1 and x2 axes, you could plot it in an r and theta axis. So you make some kind of radial symmetry. So you've got one, so you end up with two blobs, one at radius 1, one at radius 2, and the theta would then be all the way around, so you end up with two vertical blobs. That you could then cluster and get the right stuff working. In essence, that's what some of the other clustering algorithms that have worked here have done. They've done various transformations to the data implicitly in order to make the data more easily clusterable. So what I suggest you take away from this is A, if your data isn't going to work with k-means, either pre-process it with some kind of transformation, whether it's logging your data, making it radial, or using PCA, or consider using a different clustering algorithm and see which one works best for your data. So we're going to move on to the last section here, and that is using clustering for something which isn't just plain old data, but is something a little bit more visual. And so I'm going to open up a new new notebook. And we have 15 minutes left, and so I'm largely going to go through this and explain what I'm doing along the way. And I'm going to leave the exercise at the end, probably as homework exercises for you. So we're going to start off by loading in a photograph. This is a photograph from Wikimedia Commons, and so it's openly licensed under Creative Commons. And we're on a new line, and we want to print out how big this picture is. So scikit-image is a sister project to scikit-learn, which deals with loading images. With io.imread, you can just load a JPEG from a URL and you get access to it as an array on your computer. So let's have a look at this. It's a photograph which is 480 by 480 by 3. It is 3 at the end. It's a three-dimensional picture because we have a separate 480 by 480 matrix for red, for green, and for blue. So it's a cube of data, 480 by 480 by 3. And the fact that that's 3 is going to be important as we go through this. But let's have a look at what the picture actually looks like, because that's what we really care about. Show, another function from the scikit-image.io library. And let's plot the picture. And we get a rather nice picture of a swallow-tailed bee-eater bird. Again, I'm not an ornithologist, so I don't know any more about it than that, though I guess they probably eat bees. By default, the data in these images is ranging from, each value in the matrix is varying from 0 to 255. It's conventional to normally transform your data so that it goes between 0 and 1. Many machine learning algorithms just work a little bit nicer like that. You get normalized data, things end up just working a little bit better. So let's go ahead and scale our image by taking our data, loading it into an array. Oh, I need to import numpy. Loading into array with a data type of float, and that's because when it was a 0 to 255, it was an integer. We want to convert it into a float so we can represent it between 0 and 1, and then we divide it by 255, and we're just going to overwrite the same variable. So it's the same picture, it's just all been made effectively much darker, but it's all got the same relative values. We then want to extract out the shape of our photo, because later on we're going to be changing the shape and we want to be able to reform the shape. So photo.shape returns the width, the height, and the depth of the image. That's 480, 480, and 3. We're going to save that in a tuple called original shape as well, and we're going to pull it out there. Once we've saved what the original shape of the image is, we are going to do something to it, where we are going to reshape it from being a 480 by 480 by 3 image, and we're going to change it so that the spatial dimensions just get thrown away. We are going to stop caring about where the pixels are, and we're just going to keep track of what the pixels are. So we turn it into something which has one dimension, which is width times height, which is going to be some number of thousands, and another dimension, which is the depth. And I'm going to save that as image array. And let's have a look at what that looks like. So here we see there is an array here, which has got red, green, and blue values between 0 and 1 for the first pixel, red, green, and blue values for the second pixel, red, green, and blue values for the third pixel, and so on until the red, green, and blue value for the last pixel down in the bottom right-hand corner. So this has effectively taken our picture here and has flattened it, so instead of being two-dimensional, it's just one long list of pixels, each of which has a red, a green, and a blue value. And that's because we're going to apply clustering on this, and we're not going to do spatial clustering in the sense of find out a pixel and then the pixels that are near it in XY space. We're instead going to find out the pixels that are near it in color space. So if we find a pixel that's yellow, we're going to try and find all the other pixels that are yellow. And we're going to try and make a yellow cluster, and a green cluster, and a blue cluster. And the reason we're going to do that is because if we can represent our bird with fewer number of colours, at the moment this bird is represented with 16 million colours or something. If we can represent it with fewer colours, one green, one blue, one yellow, while the picture becomes less nice looking, it also becomes much, much smaller in terms of memory usage. And so effectively what we're doing is creating a compression algorithm, something which can make our pictures smaller in memory, which means you can email them to people more easily and so on. And that's something we can do with clustering. We've got our image array here, but we want to stick it into a Pandas DataFrame because then we've got column names and it will look something like this. A table with 230,000 rows because there are 230,000 pixels. Each pixel has got a red, a green, and a blue value. Once we've got those red, green, and blue values, we want to have a look and see how they're distributed. Now, red, green, and blue, you can plot it in one of two ways. You can plot it as a photo by using the red to change the amount of red on a pixel, the green the amount of green on a pixel, and the blue to change the amount of blue on a pixel. Or you could plot it as a cube with red on x-axis, green on the y-axis, and blue on the z-axis. And that will give you a sense of how the different pixels are distributed in colour space. And so we're hoping that all of the yellow pixels will be globbed together in one space in this cube, all the blue pixels will be globbed together in another place in this cube, and we'll be able to make that into a blue cluster and turn all the bluish pixels in the original image into that blue colour, therefore reducing the amount of different colours in the image, therefore reducing the memory usage. In order to plot this data, matplotlib doesn't understand 3 columns with different integers inside them, so we have to do a little bit of trickery, and I'm just going to copy and paste this. I'm not going to worry too much about how it works, but effectively it's creating a new column called colour, which has a hexadecimal representation of the colour made out of the red, green, and the blue values. So here we've got the red, the green, and the blue, and we've got a new column, which is colour, which has got 69 representing the amount of red, 64 representing the amount of green, 46 representing the amount of blue, and then 60 representing how transparent we want it to be. So this is RGBA hexadecimal code. The only reason we're doing this colour column here is for plotting purposes. This isn't going to be used as part of the clustering. We're just doing this to be able to draw a picture. Now, before we can draw a picture, we've currently got, what did I say there were, 230,000 pixels. That's way more than we need on our plot. So let's go ahead and take a subsample of our data randomly so that we've just got fewer pixels to worry about. So I'm going to take 5% of the data. So pixel sample is just taking a random subset of our pixels. So instead of having 230,000, we'll have 5% of 230,000. We can then go ahead and plot it. Feel free to have a look through this code later about what it does, but it passes in the samples, it tells us which columns we want to plot, and then it plots each of those pairs of columns against each other. So it's going to plot red against green, red against blue, and then green against blue. And so when we have a look at this, we get our scatter plot like we had for our iris example. So we have here on the first plot, red on the x-axis and green on the y-axis. So we were hoping that we were going to be seeing distinct blue blobs, yellow blobs, green blobs, but the most thing we're seeing is there's a big streak of sort of browny purple through the middle, and that's because the majority of the original image was background and the stick that the bird's on. So we're hoping that's not going to affect our stuff too much, but we'll have to see. But based on this 3-dimensional data here, this no longer is a photograph. It no longer knows where the pixels go. It just knows how many of each pixel there are and what their values are. But because we've got some multi-dimensional data, we can just throw k-means at it and see what happens. So let's load in our k-means and then call k-means n clusters and underscore equals something. So at this point we want to choose how many colours we want to end up with. Now a photograph by default has got something like 16 million colours, 256 times 256 times 256, whatever that is. We want to reduce it down to something much, much smaller. For now, because my computer won't survive otherwise, I'm going to do 10. I ran this course last week, and when I tried to do 100, my laptop broke, so I'm not going to be doing that again. But we're going to try and cluster this data here with 10 different clusters and see what clusters it finds. And we fit it with our pixels subsample data, because we don't need all of our data. The 5% data is enough. And we're going to use the red, the green, and the blue columns. And we save that to a variable. Now this will take a little bit longer. It took maybe half a second. If I try with 100, my computer ran out of memory. Let's have a look and see which clusters it found. So we do that using k-means.clusterCenters, same as before. This is going to be a 3-column data set, which is going to be the red, the green, and the blue center for cluster 1, the red, the green, the blue center for cluster 2, the red, the green, the blue center for cluster 3, etc. But let's do a graph of it, because otherwise we won't be able to see it. In show. I'm using matplotlib here to draw a graph of that data. So you see here, these are the cluster centers that it's managed to find. Our original bird, I'll just scan back up to it for a moment, had yellow, green, and blue as its main feather colors, and the rest was kind of brown for the background. our cluster centers from our data there has found a bluish one at the end. It's found a kind of muddy yellow in the middle, and it's found a grassy green at number 8 at the end. So it's kind of found some main colors, but you see the majority of it is brown. Using these found clusters, what we're going to do, we're going to replace, for each pixel, we're going to look up what the red-green value of that pixel is in the original image, work out which cluster center it's nearest to, and replace it with the value of that cluster center. And then we're going to plot that picture and see how it looks. So we do that by asking it for its labels, same as we did before. We are going to call the predict function. We're going to pass in all the pixels from our original image, and we're going to get back for each pixel in our original image the cluster center that the k-means algorithm reckons it's nearest to. And we've got a whole bunch of 5, 1, 1, etc, etc. There'll be numbers between 0 and 9. Once we've got that, we can go ahead and reshape it back to being square. So remember, our pixels was taken from being 480 by 480 by 3 to being some long list of numbers by 3. So we're going to put up our cluster centers back into the original shape and then have a look at what that looks like. So first we'll run reduced. And what I'm going to do is a plot of the original picture against our reduced picture. And you see here, it looks kind of ugly. But in terms of memory usage, this image is going to be thousands of times smaller to store on disk, and we're only using 10 different colors to do so. So what we can do with that, we can go up and we can have a look at how it looks if we change this to 15. I'm going to be cautious because I don't want my computer to break again. That 15 worked absolutely fine. And we run this and we're going to see that that picture on the right should become a bit better looking. Some yellows have started appearing, which they weren't showing up properly before. So as we increase this, we'll slowly get better and better representation, but we're going to get there a long time before we ever get to 16 million. This is actually often used as an artistic tool to make nice looking pictures if you choose your spatial orientation correctly. With the remaining few minutes, I'm just going to show you very quickly another technique that you can do to make your representation look a bit better. I'm going to change this back to 10. So I'm just going to copy this code in for demonstration purposes. So what we're doing here is we're going to take our red, green, blue scatter plot and we are going to perform a transformation on it by changing what's called the color space. So instead of representing each pixel in terms of how much red, green and blue it has, we're going to represent it by how light it is, which is what L stands for in lab, and how much of two other parameters it has. You can kind of think of this as doing a principal component analysis on it. We're then going to reorganize our data and look at what our new projection of 3D space looks like. So here we have the same data, but transformed mathematically into a different representation in 3D space. So instead of red, green, blue, we have L, A, and B. And you see here the clusters are much better distinguished. All that brown is no longer a streak through the middle, it's a blob. So hopefully that will be clustered more effectively. The yellow is distinct, the green is distinct, and the blue is distinct. So that means if we go ahead and ask it for a clustering of that data set, again using k-means fit of this new data, and have a look at what the clusters look like, we see we've now got slightly more variation in colour. We've got two different types of green and yellow and blue. Still got a lot of brown, but right now there's not a lot we can do about that. If we want to have a look at what our original bird transformed onto this clustered set looks like, we can do that. And here we see a different kind of reduction happening. With only 10 colours, it's got all of the main colours, two different greens, a blue and a yellow. But you see it's reduced the colours in other directions. Best way to see this is to plot all three of the pictures on one plot together. So here we have the original picture on the left, the RGB with 10 clusters in the middle, and the lab cluster with, again, 10 clusters on the right-hand side. Now, there might be pros or cons to one or the other, but certainly the one on the right-hand side has managed to pick out more of the interesting colours, whereas the one in the middle hasn't managed to find the yellow at all. So by choosing a appropriate transformation for your data, you can sometimes find more representative blobs which are telling you interesting things about your data. For example, the middle one never found the yellow, whereas the lab cluster does manage to find the yellow. So we're basically at the end of the session now. So after the session, feel free to have another little scan through this page. There's some exercises at the bottom, which I'll leave for you to do for homework. So do have a go at those. And I'm just going to finish off with a bit of a summary as to what you might want to look into next. So this course has covered linear regression and clustering on the whole, but there's some other techniques which are really useful and can solve simple-ish problems but can be very powerful. One of those is naive Bayes, so it's worth having a read into that. That's a way of saying if the data was generated, how was it generated and what would the distribution look like. Support vector machines allow you to draw lines and separate your clusters of data, which is a really, really nice way of deciding how you should classify your data. Principal component analysis, I've mentioned. And neural networks, we have a course called Intro to Deep Learning, which we'll be running sometime in the future, so feel free to keep an eye out for that. And I'll finally point out some further reading you might want to look into. So the Python Data Science Handbook by Jake van der Plas is a really, really great book. It's free online. Do have a look at that. The scikit-learn documentation's got lots of interesting pages describing how these techniques work. And if you're looking for a good book to talk through this stuff, right from the very basics through to advanced data analysis techniques, I very, very strongly recommend Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. I suggest you get the second edition if you can, which came out about a year ago. It's a really, really good book. It teaches almost everything you need to know about machine learning, data science, and data analysis. So do go ahead and grab that if you get a chance. With that, I'm just going to say thank you all very much for coming along to the session today. We got through a lot of stuff, so I hope hopefully it hasn't been too quick, but it's been really great having you all along, and I hope to see you again in another course in the future. Thanks and goodbye.